Good morning, Mungode sir.
Very good morning. I think almost 10 तर वाजलेत.
Yes, yes, yes.
मला वाटते रिसोर्स पर्सन काही जॉईन झालेले नाहीत.
हा हा येत आहेत आम्ही बोलणं झालं त्यांच्यासोबत. Good morning, Reddy sir. Good morning, German. Mino Galas.
Good morning. Good morning. How are you?
I'm fine, sir.
Here it's 1:32 a.m.
Oh my God.
I'm just about to go to sleep.
Yeah. No problem, sir. No problem.
Nice to say hello. Nice to say hello.
Thank you, sir. Good morning to all of you who are present in the day 2 of this session. Good morning, Dev sir. Our chairman and resource person are about to join, so we need to wait for some time for the technical session. Within 5 to 10 minutes, we shall start the technical sessions. Good morning, Michael, Professor Michael, sir.
Good morning. Can you hear me?
Yeah. You are audible, sir.
I cannot start my video because I had to enter as. Now it's.
Yeah. Now you are visible also.
Okay, great. I was a little bit worried because the link did not work out as I hoped.
Okay, fine. Sir, our today's chairman is about to join, so we need to wait for some time.
This is good. Then I have some time to wake up. It's also 5:35 in the morning now here.
Yeah.
It was very difficult to enter the link. It doesn't work well. I also have some problems to enter.
Requested some verification code and then it was not working, so I had to. But yesterday when I joined, it was excellent just to click and join.
Okay. And it may be because you have joined from the forwarded link, I think.
Could be.
Good morning, Professor Michael.
Good morning.
Sir, how are you?
I'm fine. It's early bird.
Yeah.
Hello, am I audible? Yes, sir. Good morning, lad, sir.
Good morning.
Now our chairman for this today's first technical session, Professor Ajay Lad, is present here, and our today's resource person, Professor Michael, is also present. So I request Lad sir to uh, chair the first technical session. Sir, Lad sir, please you proceed, sir.
Yes. Good morning, all of you. Good morning, Dr. Michael.
Good morning.
26th International Conference on Advances in Physics in collaborations with the International Academy of Physical Sciences, Prayagraj, organized by the Gondwana University, Gadchiroli. This is the second day of the conference. Firstly, I am very grateful and thankful to the organizer to provide me opportunity as a chairperson of this session, which is delivered by renowned resource person Mikael Sikosti from Longping University, Sweden, and another professor Shukla sir from the National Institute of Technology, Mizoram. Very good morning, both of you and all participants. Firstly, I introduce Dr. Mikael from the Linköping University, Sweden. Dr. Mikael sir has started research since 1995 in growth of energy and environmental material such as silicon carbide and graphene. Since 2005, active in creating transfer to promote research and innovative reach commercialization from research finding. Founder and co-founder of several startups and communicates networks. Today, Dr. Michael delivered the talk on advances in physics facilitator of invention. Sir, please start your innovative talk. Sir, you have 40 minutes.
Thank you very much for this kind introduction, and thank you very much for inviting me to present at this event. And since a few years, I have been working to establish the Sweden-India platform for exchange. And the hope is that there will be new ideas for research and innovation which are natural, and then they grow over time and so on. So I'm very used to this time difference, which is between India and Sweden. So now it's early in the morning in Sweden. And what I will do today, I will not go in deep into any topic which I have explored during my years as researcher since 1995. But what I will do is to give an indication that the research findings may be useful, come to utilization, be commercialized in different ways. And the message will be that there is no clear route how to commercialize some research findings, because we are usually at the very beginning, we have new ideas, new innovations, and we have an assumption that it will work here. But like in many cases, we find that it doesn't work exactly here, or maybe a part of this will be the one which is possible to utilize. If we look at the different physics and science studies over the years, they have been useful at some point in other applications than the one we intended. So now I will share some of my experiences in this from the research. So now I hope you see my screen, my presentation.
Yes, sir. It is visible.
That is, yes, great. So I will talk about advances in physics as facilitator of innovations. And like I said, physics and the things we're doing in research, we are usually very much in a new position. There are new things we're exploring. We're not studying the research to do things which have been done before. So we'll do something new, and that can be a facilitator for the innovations and later on something which can be commercialized and be useful for the society. And to give an experience from my background, what I will talk about is that I work with silicon carbide growth, and that is the traditional way to grow this silicon carbide is that you have a source, like at the bottom here, containing of silicon carbide powder. And when you heat up this to a very high temperature, then there are vapor species of silicon, silicon carbon 2, silicon 2 carbon, and so on. And those are transported to the growing surface, and the material is growing. And this is the schematic of the traditional way to grow silicon carbide for bulk material. And in the 90s, when I started as a researcher, this was very new, so there was not so much explored at all. And the intention was to grow bulk material and cut out wafers and polish them so they could be substrates for epitaxy and device processing. But at that time, 90s, it was very many things which were new in the research of the material. But now, silicon carbide is very mature. There are several commercial suppliers, and there's even a market which is growing very fast. And in my studies, we applied this traditional bulk growth method, but we also modified this method that we shortened the distance between source and substrate, and we lowered the temperature, and we lowered the background pressure, which is used to control the vapor species. And then we came into a modified version of this growth. And then it's epitaxy. And the benefit here is that it's possible then to use the high growth rate and grow thick layers of silicon carbide. And at that time, it was motivated because power devices need very thick layers, the more voltage they convert. And we were able to grow thick layers of silicon carbide on the wafers. So here you see in this inner circle, there is about 100 micrometer thick layer, a thin film of silicon carbide on the wafer. So this was very good achievement at that time. And if we go back many years, now the main motivation for silicon carbide is power devices and MOS devices, which are in the electronics. But if we actually go back to one of the first, or even the first notification of silicon carbide to study, there was a paper in 1907 in Electrical World that H.U. Round was exploring silicon carbide material. And when he had contacts to them to make a electronic device, then he could observe that there was light coming out from the silicon carbide material. It was blue, green, different colors, and so on. So this was one of the first presentations of light-emitting material. And silicon carbide is an indirect band gap material, so it's not expected. But at this time, the growth methods were very rough, so the quality of the material was not good and so on. But it was the first observation. So, 100 years later, Satoshi Kamiyama at Mayo University came into this avenue of LEDs, and he comes from the nitrides and the team at the Mayo University, where they explored the blue LED, which was later used to create the white LED using the phosphor. So he was thinking about this and thinking that if we have this material, and at that time it was uncontrolled growth, there were background dopants and so on, so it was no control at all. But he was thinking, if we take this material, which is now very mature, and we grow it in an intentional way, and intentionally we introduce these elements which provide the luminescence, then we can have a controlled recombination to get light out from silicon carbide. So that is a donor to acceptor pair recombination. So if we fully understand that one, it can be a new type of white LED. And the basic principle is that when you have donors and acceptors, you have recombination between them. And since this is a donor acceptor pair luminescence, there are several levels between which the transitions can occur. And then you have a broad band instead of a sharp one, like in a p-n junction. And if you do this in 2 layers with 2 different acceptor levels, you get 2 broad bands. And if you do this one in 6H silicon carbide, the 2 broad bands come out in the visible region. So that was a new type of LED, and it also emerged to a new type of research because it has not been explored before. So in that way, this luminescence, which was unintentional 1907, when it's controlled, then it can be a new type of LED. And for that one, you're using the thick layers of silicon carbide. And in my case, at Mayo University, they are not so experienced in growth of silicon carbide. Since I had developed in the team, in the research group, we had developed this growth method. Then we started a new collaboration. So that's how I came into this avenue of fluorescent silicon carbide for white LEDs. But I'm not an LED person, I'm more growth. So then it came an opportunity, and now that is being explored to devise, and also there's a joint venture in that one. But it was not the plan from the beginning, it just emerged as a natural way from the interest in the physics and research and so on. So that became an opportunity, and still is an opportunity because it's so many things still to develop. And in this LED, the benefit is that when you have these 2 layers with 2 broad luminescence features, then one is more in the yellow region and one is more in the blue, and they are broad. When you mix them with 2 layers on top of each other, then you can have a pure white light. So these coordinates, they show that when you mix these things in the proper way, you can come into the pure white light luminescence. And in case of silicon carbide and LEDs in general, today when you have a blue phosphor, which is blue LED, which is converted by a phosphor, then you still have a blue tone, which is penetrating. So it's difficult to have a pure white light. So here you see that on the left side, you have a very efficient blue LEDs with phosphor. So they can be efficient, but the tone is still blue. And when you modify those to make better light quality, so it's more white, then you need to make compromises and efficiency goes down and so on. So this silicon carbide LED has fairly high efficiency and also pure white light. So it's unique in its way. So it's not competing with the existing LEDs and so on. So it became a natural complementary LED technique, or hopefully to be developed to a full LED technique. Now it's still very much on the material development and understanding what is really happening. And just to give a flavor what is the main thing, This is to study how much of these dopants should we introduce to have an efficient luminescence, and which is the balance between donors and acceptors. So then we are studying the difference and how much luminescence intensity we get. And then we need to go into the details on the atomic level. But this is a challenging area, but it works. So we have some examples of light. So here you see two near UV LEDs, and those are used to excite the silicon carbide. So on the left side, we have not so much progress, but over time, then we can actually have light coming out from the silicon carbide. So on the right side, you see that there is light when we change these ones, and this is one of the layers, so that's why it's yellowish. So it's not the theory and so on, it is practically that we can observe the luminescence at room temperature from silicon carbide. So this is very exciting. And then in the background, you see an TEM image of the atomic position. So we still need to understand those things, how the luminescence can come out. And there are many different possibilities of how to kill the luminescence in the material. So this is still a big avenue for exploring in the research. But if it works out to the full extent, then it can be an LED technology which has impact in the society. So that became an possibility of innovation, which we were not planning from the beginning because we were interested in the physics, growth, and research. And then we are studying the different conditions, how to control the growth and do the doping at the same time, and to keep the smooth surfaces on which there will be a nitride layer grown to create near UV, which excites the silicon carbide. And this led to a very nice collaboration. So over the years, we have had quite many workshops to discuss these things. This research, in my case, started 2010. And then we have had various workshops over the years together with partners in Europe. And also the collaboration with Mayo University has been very nice. So it works out. So there is luminescence from the silicon carbide. And in the future, I think that this can be a combination to resolve even new things. When we have, for example, graphene on silicon carbide, and then we add molecules to create some new exchange of materials for bio applications. Maybe we can trigger functions of the molecules by the light from the silicon carbide and so on. So there's still many things to do when we have ideas and want to explore them in the future. And another thing which happens when you have silicon carbide, when you have a wafer and you're growing a thick film, and the traditional or most normal silicon carbide is hexagonal silicon carbide. So then we have 6H layers on 6H substrates and 4H layers on 4H substrates. So that is the most explored way. But there is also the cubic silicon carbide. So this distinguishes itself a little bit from the hexagonal silicon carbide. It's still silicon and carbon atoms. So when you stack them in different ways, you can stack in one way to get the 6H silicon carbide, in a second way to get the 4H silicon carbide. And then in another way, you can, if you stack it, then you get cubic silicon carbide. So it's still silicon and carbon, but one of the main differences is that the band gap is lower in cubic silicon carbide. In the 6H and 4H, it is 3 and 3.3 electron volts. And in the cubic, it's 2.3 electron volts. So it's quite much difference for the silicon carbide family. So then the cubic silicon carbide can be an opportunity for new things. And in the beginning, in the 90s, people were growing the hexagonal silicon carbide films on substrates. And then that was the way to control this hexagonal thin films on hexagonal substrates. But what is happening is that you can have cubic silicon carbide and it started to form in the layers and so on, and then it becomes a problem. And the nucleation of cubic silicon carbide is still to a large extent unknown, because it doesn't want to form. It is metastable in some way, and people don't know the exact mechanism. So it may form, like in this case, it's small crystals on graphite in a natural way, which can be very high quality, but they are very, very tiny, just a few millimeters, a couple of millimeters. And you can also grow this cubic silicon carbide on silicon, but then you have a mismatch between silicon and the silicon carbide, which creates a lot of problems. So you can use the wafer size of silicon, but it's still many defects in the material, like you can see in this image of. And also the silicon carbide on silicon has a mismatch in the thermal expansion coefficient and the lattice parameters. So then it creates stress, which bends the layers. So it's very challenging to grow the cubic silicon carbide. But we have been using our modified technique. When we lower the temperature and so on, then we could get cubic silicon carbide to form, and we have studied it over some years now. So that became an avenue. So instead of having inclusions in the materials, we want to control the inclusions growth, so it's dominating. And the basic mechanism for cubic silicon carbide is two-dimensional nucleation. So when you have these ones, you have domains which are forming, and then the cubic silicon carbide is supposed to expand. So this is also a big avenue for research. And then simplified, one way to control this is that you have cubic silicon carbide formed on planar surfaces, and then we're using off-axis substrates so it can expand. So that's a way how to make the domains larger of the cubic silicon carbide, because usually they are very tricky to form, but it's also very tricky to get large domains. And if you don't have large domains, you have never good quality. So here we studied some different temperatures, because that is one of the parameters, and also the difference of the off-axis of the wafers to see how much cubic. And in this image, the yellow things is the cubic silicon carbide. So you can see on the different changes that we have various amounts of cubic silicon carbide, which is formed on 6H silicon carbide, which we use as a substrate. And then we want to get cubic silicon carbide on top of it. And this research has, of course, been mainly done by the PhD students. So Remigius Vasiliauskas was one of the first in the previous image, and then we have Valdas Jokubavicius. And then when we explored these things, we could see the different domain sizes and how much free C do we get and so on. And its influence from the temperature and so on. So this is still very much to explore. And we have a couple of papers which can be read about these things. So it's very nice from the growth point of view, but we should also have some application which is attractive for this. So when I had this fluorescent silicon carbide research 2010, and then in 2011, I was invited to go to a Nordic semiconductor meeting, and then I presented my talk. So I had an invited talk on the fluorescent silicon carbide because it was a very new topic. And then I made my presentation and went down and sat. And then the next speaker came up. So Antonio Marti from Spain, he and his colleague, they actually proposed. So he made a presentation about the solar cell. So in a material, if you have sufficient large band gap, and you introduce an intermediate band in that band gap, then you can have actually 3 different transitions or absorptions in one single material. So instead of having 3 layers with different band gaps and 3 different materials, which are difficult to grow together and on top of each other and so on, then you can do this in one layer if you introduce, so you get an intermediate band. So that they proposed in the paper, and also, and then when you have different energies, then you can collect different parts of the solar spectrum and have much higher efficiency than in a single material. So this was a theory, and in this theory, when I looked at what do they use, they have a certain band gap, and this band should be at certain level. And the cubic silicon carbide, since it has a lower band gap, it suited very nice into this theory. And also the boron which we were using to dope the fluorescent silicon carbide, that also had a suitable level for this. So then we came into cubic silicon carbide as a solar cell material or solar material. And actually there was one paper which proposed this some years ago. And then they said that this effect, so they made similar theory in wide band gap materials, it could be an opportunity. And that there, the cubic silicon carbide is an example of a potential. So now from the growth interest and our new interest in the optical properties for the fluorescent light emitting, now we came into another avenue of using the cubic towards solar function. So that became a new innovation. But it was not, again, it was not a plan from the beginning. It just emerged because we were interacting in the at conferences and other places, and then we heard about new things, and then some new things just emerged naturally from our interests. And also, I will not go into detail, but actually, the properties of the cubic silicon carbide is also interesting to have hydrogen generation by water splitting. So there are some things about the positions of the conduction band and valence band, where they're located, and the size of it, and also how much is the mobility of the electron and hole, and so on. And it should also be corrosion resistant, as silicon carbide is known for that. So then actually we could initiate research in hydrogen generation by water splitting using the solar energy only. So one of my colleagues is now has this idea and now explores that one even more. So then it emerged to another opportunity for another application. Originally, silicon carbide is attractive for the power devices, the electronics. So now we have some other avenues which just emerged naturally. And there, the attraction is that the mobilities of the electron and hole are high or fairly high. And that's one motivation that cubic could actually be very attractive for this hydrogen generation. And another thing which happens in silicon carbide is that when we are growing the material, by the silicon and carbon atoms, and when we have conditions so there's more silicon which is lost than the carbon, then that graphitizes the surface. So this is a graphitization process of silicon carbide, which is not desired for the growth of silicon carbide. But in such way, one can actually grow graphitic layers on silicon carbide from the silicon carbide. So it's a natural process. And when we made this thinner, then 2005, we had one layer of carbon on silicon carbide. So that is, then we are into the graphene on silicon carbide. And now we are using this to study some new effects on tuning. So use this graphene on cubic silicon carbide as a junction for the solar applications. So then we add on materials on each other, and then we explore these new features. So it's super interesting research avenue, and hopefully at some point this can be controlled, so it can be a device which is functioning and making some usefulness. But still, it's early stage, and all who are working with the material know that it takes a lot of time before the material is mature enough for having devices which are in products. For the silicon carbide, it took 15, 20 years before the first activities in the 90s became mature enough so you could have a market in silicon carbide. But now it's there, and the good thing is that then we have more cheap substrate and wafers which we can use for these other ones, other applications which are still emerging. And like I mentioned, this takes a very long time. So we had these first observations 20 years ago when I was presenting a paper at Cluster Banz in Germany. It was a silicon carbide conference. So then we had the initial cubic silicon carbide, the yellow parts here, on a poor wafers which we were using as test material. So still, we are not in the mature stage. But it's fascinating research, and hopefully there will be some innovations from these findings. And what is happening in reality is that you cannot sit in the office and have all the innovations and ideas just popping up. Not even from reading papers, you can really get the ideas. So the most useful activity for this new innovations is that you interact with people, you discuss, you go to labs when you are visiting, and then you see some new things which you did not know, some things maybe you knew about, but then you understand some detail a little bit more, what they are doing in the labs, in their research. So this interaction is very useful. And of course, at conferences, you have the physical interaction, you can drink coffee, so these informal times between presentations is also very useful. And this is also the hope with these online conferences, because now we have the video tools, we can present like this, and there will be a question and an answer, and there we can have the interaction and still get personal contacts because there's video and so on. So there can be new ideas, and we can use the digitalization to facilitate even more things to happen. And even if we have one idea, we always need a value chain, and this will not be in the same country. So then we need to find international partners for the various things. And this is what we are doing with like Sweden, India. We have the graphene on silicon carbide that can be used towards sensors, but also the interaction with the molecules, like in bio applications. That is a new growing avenue which we are very interested in. And some things which are happening in the world is that when you have these ideas, and here is Professor Amano at the European MRS, and he was one of the Nobel Prize winners for the blue LED. So Isamu Akasaki was the original one, and then there were different contributions, and that's why there were a Nobel Prize in the blue LED to 3 persons. And the initial research started many years ago, 70s, 80s, and then you had the blue LED commercialized 93, and then you added the phosphor, and then it took 30 years before the white LED, based on the blue LED and phosphor, became a product which contributes to the society to a large extent. So it's a key enabling technology. But it took more than 30 years. And now when the funding agencies would like to have even more of those key enabling technologies and the new ideas, then it will not just grow naturally from research interest. So like in Japan, what they're doing is that when the funding agencies would like to have these technologies, but not in 30 years, they would like to have it in less than 10 years, which the researchers said, oh, no, it's not possible. Maybe we can find a balance here. But then what they're doing in Japan is that they have programs for this. So students who would like to become entrepreneurs, they are supported and encouraged. and those who would like to develop the research findings into production to make the findings reproducible, so it can be produced. Those are also supported. And those who would like to explore new technologies, they also supported for these things. So based on the interest, they are encouraged to continue to explore the different things and towards innovations. And in Japan, there is a mentor program, internships. So it's a big program overall, which is happening. And this is similar what in Europe, there are some things which are happening. And in my belief is that if we have the technology development and technology motivations, that produces a value chain from technology point of view. But in our regions, the regions would like to have more economic growth, and then they facilitate those and find things where there's more activity. And at the end, that will mean that it's value chain in some certain field. So if these two are having more interactions, then there can be synergies from the regional economic development and also the technology and research. By this, I would like to say that we should also be aware of the other things which are going. We don't need to know them in full detail, but just having in mind what is going on the regional level, not only the atoms and physics, then we can position our research and then inventions and so on into a larger context, and then maybe we can facilitate that those things are actually implemented in reality over time. But everything of these things, it's come from the science. And we have had a few webinars and question and answer type of exchange meetings in nanotechnology for the innovation to discuss those things, because we cannot understand how to do things just naturally. We need some examples and sharing practices and someone who has an idea. So this interaction is very useful for also the how to get the innovations come to a next stage. So with this, I would like to thank you very much for listening. And the idea here is that to give this as an example, there, that in the research, there are various opportunities we cannot expect. We can make an assumption, but we don't really know where it will be useful. But still, we should continue this fascinating interest which we have. And in some cases, it's some new idea, and maybe some professor says that, no, this has been done many years ago, but still there is room how to position this in a new context. Like in the silicon carbide, it became applicable for optical properties and luminescence. So still, even if someone says that this has been done many years ago and it failed, then we should continue to do this. So this is an encouragement to the students to not always listen to the professors and so on. They have very valuable things, but still having the interactions and testing things in reality, go to the lab, grow some things, understand, and so on. So this is a facilitator for innovations from the research. So I hope I have given a couple of examples from my own experience in these things, and now I would like to have question and answer and discussion and interaction. So thank you very much.
Thank you very much, Dr. Mikhail Suzarvi. Dr. Mikhail, and nanoparticles. Related emissions, LED, and also growth and small size of the nanoparticles. And after 2005, he worked on the innovative material, silicon carbide and graphene, and is useful for the solar junctions, sensors, bio applications, He has given details about the all particles related to the nanoparticles. He has explained very simply language and give the very informative and innovative talk. Thank you very much, Dr. Mikhail. You are take
Yes,
proper time
thank you very
for
much.
40 minutes. Thank you very much. Thank you. Thank you. Any queries from participant, send to the organizer. They will contact Mikhail sir. Thank you. Thank you very much, sir.
Yes, thank you very much. I'm very happy to collaborate because I think there are always complementary interest and things, and that will be international. So Sweden, India is one of the things I'm very active for. So thank you.
Now, next session, Dr. Alok Shukla sir. Dr. Alok Shukla sir is an associate professor in physics, National Institute of Technology, NIT, Mizoram. He taught engineering physics and material science at NIT, Mizoram for many years and undertook research in multiphysics. He has guided 2 students for PhD degree and 4 students are working under his able guidance. Dr. Shukla has about 40 research papers in international journal of repute. He visited various countries for research work. Presently, he is working on development of nano-size multifluidic material under ACRB funded research project. May I audible Dr. Alok Shukla sir? Dr. Shukla sir?
I think he's joining in few seconds. Okay, so
Okay.
Dr. Shukla is about to join. He is facing some technical problems. So he will be joined within 5 to 10 minutes. So we shall wait for it. Yeah, we shall wait for it.
Okay. Dr. Sandeep sir. At 10:30 I have meeting.
Sir?
10:11:30 ला मीटिंग आहे माझी.
Mhm.
तर
Okay,
यांचं
okay.
सरांचं कन्क्लूड करून द्याल हा चालेल ना?
हो. नो इश्यू सर.
बरं हा चालेल ना म्हणजे मी सुरू करून देतो.
हो ते जॉईन होत आहेत. थोडंसं वेळ लागेल. त्यांना इंटरनेटचा
हो.
इश्यू चालू तिथे.
हा नेटचा प्रॉब्लेम राहतच. मिझोरामकडे आहे ना ते.
हो.
हा काके सर. हॅलो काके सर.
येस सर, येस सर,
हॅलो.
येस सर.
काय ब्लँक काउंट झालेला आहे?
ब्लँक सर काय झालंय की शुक्ला सरांशी मी कॉन्टॅक्ट केलाय. त्यांच्या इथे थोडा इंटरनेटचा प्रॉब्लेम चालू आहे, तर ते थोडं वेळ त्याच्यामुळे तो फिरत आहे म्हणे, फक्त दाखवत आहे की अबाउट टू जॉईन.
गोल गोल फिरताय म्हणे का?
हो हो हो.
अच्छा अच्छा.
तो ते म्हणाले की
फिजिक्सचा प्रोफेसर नाही हे नाही का? हम्म.
ठीक आहे, मग वेट करूया एक 5-1 मिनिट सर, कारण की आता ते इंटरनेट कनेक्टिव्हिटीचा इश्यू आहे त्यात आपण.
हो 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 हो. कनेक्टिव्हिटीचा इश्यू असल्यामुळे तो काही विषय नाही.
हां हां हां.
हा सुनील नाही आज?
आहे आहे.
आहे ना?
हो सर.
I think Professor Shukla had joined. Next technical session will begin in very short time. Professor Shukla, sir, am I audible?
Yes, sir.
Okay, sir.
But I am unable to share my slides.
Okay.
I have already uploaded actually. So can you check it from your side also?
Sir, it is not visible.
Not visible?
Yeah.
Sir, Shukla sir,
1 minute, sir. We'll allow you to share. Then I
Okay.
think, okay.
Hello. Yes. Sir, I have joined, but I am unable to share my slide in the this one Webex. Huh. You have sent it to different email. Huh.
Chagan, communicate. हॅलो.
हा सर, कागे सर बोलत आहेत त्यांच्याशी.
Your voice is also not clear. Just wait, I call you back.
शकत नाही तर असं करा, त्यांच्याकडनं मेलवर पीपीटी मागून घ्या.
हा, तेच सांगत आहे सर सरांना की पीपीटी शेअर करा आमच्यासोबत, आम्ही प्रेझेंट करू आणि मग सर प्रेझेंट करतील.
अच्छा, असं सांगत आहेत
सर
त्यांना.
बोललो मी त्यांच्यासोबत, पण ते त्यांच्या लक्षात नाही आलं. इथूनच सांगावं लागेल मग मला वाटतं.
नाही इथं नाही, त्यांना म्हणा वन्स सेंड कर, कोणत्या मेलवर पाठवली आहे ते विचारून घ्या.
पण ठीक आहे सर.
नाहीतर आता या मेलवर पाठवून द्या म्हणा.
मी त्यांना सांगितलं, पण बहुतेक ते त्यांचं प्रॉब्लेम येत आहे, रेंजचा इश्यू आहे काहीतरी बहुतेक.
अच्छा, कनेक्टिव्हिटी इश्यू आहे. ठीक आहे, पहा 2-4 मिनिटं. Hello, Shukla sir.
Yes.
Sir, what's the problem? Connectivity problem?
Yes, sir. Yes, sir. Still, I am unable to upload my slides.
Yeah, so it is better to send out email.
Yes.
You just send it out email.
Okay.
CONIAPS. So that we will share the slides from our side. You can only talk.
Okay. Sure.
So you just mail now your PPT.
Okay. Sure. Just wait within minute. I will do.
Okay. Kage sir. Hello. Kage.
येस सर. अनम्यूट केलं, म्यूट केलं.
ते शेअर करतात आहे मेलवरती.
हो, मी ते प्रेझेंट करतो सर इथून.
तिथून प्रेझेंट करायला.
हो.
त्यांना विचारून घ्या की कोणत्या मेलवर पाठवलं.
हो.
ते शेअर करतायत ते
हो
मेलवर.
सर.
ढोबळे सरांचा वेळ होऊन जाईल म्हटलं.
Yes, sir. I have sent.
Okay, you have sent PPT.
Yes, sir.
I will check. I'll check, sir. I'll check.
ओके चेक करा. On which mail, sir?
In your that register mail, gug.register@gmail.com.
GUG.register. GUG.register. Oh, I see. Okay. हाँ कागे सर. हेलो. हाँ कागे सर. कागे सर. हेलो कागे सर.
Kage sir is not present, sir. Check the mail.
कोण आहे तिथे?
Sunil,
Sir,
Sunil.
I will convey. I will.
हा सुनील.
हा.
हा कोणी कोणी SPS
हा,
मेल पर मी फॉरवर्ड केले आहे. तिथून
हा.
डाउनलोड करून शेअर करा ते.
ठीक आहे. कोणी SPS वर फॉरवर्ड केले?
हा CONI.
हा हा, माहित आहे.
हा माहित आहे ना तो. यस आहे, यस वाला.
हा, येस.
त्याच्यावर फॉरवर्ड केला. मिळालं का?
लॉग इन करता येईल.
Sunil. Sunil. Sunil.
कागे सर. हॅलो.
We got your mail, sir.
हॅलो, मुंगोळे सर.
Okay.
प्रेझेंट सर.
Is it visible, sir, now?
Yes, sir. Yes, sir.
Okay. Shukla, sir, now you can make your presentation.
Yes, sir. Now it is visible.
Okay.
Okay, sir. Thank you so much.
Welcome, sir.
Okay, so good morning to all. Sorry for the delay due to poor connectivity here. So I am thankful to Dr. Mohille and Vishal for giving me an opportunity to share our work. So the title of my talk is Studied on Lanthanum Substitution at the Iron Site of Bismuth Ferrite Multiferroate. So actually the theme behind this investigation is that As you know that bismuth ferrite is a very popular multiferroic material, but the problem with that, some inherent property we cannot expedite it. So that's why we thought that by the substitution of some rare earth, we want to improve the some properties due to the application point of view of the material. So initially the outline was the talk, that introduction, then what we work done, conclusion, publication, and few references also. So here in introduction part, I want to share that we have prepared the lanthanum doped bismuth ferrite by using the solid state reaction method. Then after that, we put the XRD analysis. Then what are the investigation, didactic studies with respect to temperature and frequency, impedance analysis, then conductivity, and then ferroelectric and ferromagnetic property of the prepared sample. So as you know that in methodology, solid state reaction method, we take generally oxides, binary oxides as a raw material in stoichiometric amount. Then we prepare the powder, done the calcination, then phase confirmation through XRD. If we got the confirmed phase, then we prepare the pellets, then sintering and finalize the characterization of the prepared samples. Next. So here what we used here for XRD, we use Ricago, then morphological, FESAM, we use Carlsite, then for elemental, we use EDX Oxford, then dielectric and impedance measurement, N4 PL PSM 1735. Then for ferroelectric loop, we have used P loop tracer by Marine India, and then VSM for MH loop, but Lakeshore model 7410. Here we have taken the different series of LA composition. So we start from the 0.1, 0.2, 0.3 up to 0.9. So we have characterized the different 9 sample of bismuth ferrite doped with the lanthanum. Next. So here the XRD analysis of pure BFO, where we have compared the graph in the bottom. If you will see that the blue solid line represent the difference between the observed and calculated intensity, and the Bragg locations are displayed in the green horizontal lines. So here whatever the actual peaks for pure bismuth ferrite, we have plot the XRD analysis where the component of lanthanum is 0. So this is the XRD pattern for pure bismuth ferrite. Next, sir. So here if you see that if we put the certain amount of lanthanum in it, start from 0.10, 0.20 up to 0.9. So can you see that if the enlarged view of the XRD, then this angle is increasing towards the higher side. It means if you put some lanthanum, it means some phase transition, phase change occurs place in the bismuth ferrite that we want to represent here. Okay, sir. Next. So here if you see that this what I told you earlier, that arrow recommends that the structure of BFO compound is distorted along with the variation of lattice parameter value, which suggests the structural transformation with lanthanum content. So what we can say that is such observation possess the accumulation of the rare earth ion can either eradicate the oxygen vacancies or the compositional variation of iron plus 3 and plus through oxidation state, which manipulates the presence of secondary phases. So peaks will be inclined in the direction of increasing angle. So here if you see the different XRD pattern where we have give the HKL values by using the POUT software. So each peak have assigned the certain HKL parameter values calculated by using the POUT software. Similarly, this is for remaining 3, 0.70, 0.80 and 0.790 lanthanum composition in the BFO. So if you compare the lattice parameter for all these 9 components, or the 9 component where we'll put the different value of lengthenum, so you get the different ABC value volume, and we have calculated the average crystallite size using the Sears formula. So if you can see that the minimum value of the crystallite size we found, it is around 30 nanometer, and the maximum will got it 53 nanometer for 0.80 lengthenum substitution. Okay, next. So if you see the same image, so here you get the different size and shape of the grains, which gives you some porosity here, so loose. And another, with that same image, we have given the EDX, or the elemental presence of the elements in the BFO. So here you can see that bismuth is there, iron is there, oxygen is there, and lanthanum is there with their elemental value, or you can say that stoichiometric ratio. So for all 9 samples, we have given their same images as well as EDX. Next. So similarly, it is for 30 and 40. Next. This is for 50 and 60. Similarly, 7080. And finally, this one last for where lengthenum substitution is 0.90. So here we can predict that the corresponding surface morphology of this specimen system is visualized through FESM, and this clearly depicts the most of the grain shows the submicron size, dense structure, and distributed throughout the surface of the sample. And this grain size has been measured through the image J software, and we found the grain size in the range of 0.2 micrometer to 2 micrometer for all samples. So here it shows the existence of polycrystalline nature of material also. Here we have studied the dielectric constant with respect to frequency. So if you change the frequency with the selected value of temperature for different composition, if you say that, so here you can get that at low frequency region, the dielectric constant value is more, because at that point the dipolar polarization and the space charge are the. So there is a assembly of electron which producing the large space charge polarization nearby the low frequency because of the high resistance of the grain boundary. So that is why the dielectric constant is higher at the low frequency, and as associated to the higher frequency in each cases. So here 3 figures are there: 0.10 composition, 0.20, and 0.30. Similarly, we can get it for others also. Next. So same behavior you can see that for others also: 40, 50, 60, 70, and similarly for 8 and 9 also. Now this is the frequency dependent of dielectric loss, or the 10 delta. So here you can see that the at higher temperature, due to the controlling nature of the conductivity, there is a this will be accountable for the enrichment of 10 delta. So here you see that the 10 delta value is within the certain range, like maximum 6 or 7 or below 15. So you can say that by substituting lanthanum, we are reducing the certain amount of dielectric loss in as compared to the pure bismuth ferrite material. Next. So same trend we are getting for another composition like 40, 50, 60, and so on. So now this is the temperature dependent dielectric constant study. So here you can see that at the lower value of temperature frequency, which is denoted by blackish color. So if you can say that at lower frequency, due to the all type of polarization, the dielectric constant is higher as comparable to the higher frequency of value of frequency like 1 megahertz and other. So at that higher frequency, you are getting the low dielectric constant, but at the lower frequency, the value is high due to the presence of all type of polarization. So same pattern we will get for other composition also. So similar trend we are getting till the 0.90 lengthenum substitution. This is the temperature dependence of dielectric loss. So here you see that at lower temperature, the value of 10 delta is smaller, but it will be increasing by increment in the temperature. So here again, the presence of the iron is accountable for the larger value of low loss factor at the lower frequency region. But at the high frequency, this trend becomes merged, means there will be no, though at higher frequency there will be no role, presence of iron will be not affecting the value of dielectric loss. So same pattern will got it for other composition also, you can see that. So now we come to the conductivity part. So here we can get the different value of AC conductivity with respect to frequency for the selected temperature range. So here you can simply see that this response will simply give the NTCR behavior, or you can say that it represents the semiconducting behavior of the material. So here, if by increasing the conductivity value with the rise in temperature, it proposed the NTCR phenomena, which will be explained by the Johnson law also. So we'll get the same trend for other composition like 0.20, 30, 40, 50, and so on. Here we have calculated the activation energy at the different range. You can see that we have denoted the different colors for different range, and each range will represent, and if you concentrate on a particular range, temperature range, which is from 448 K to 298 K for all composition. So here in place of NTCR, we are getting the PTCR behavior of the material that is different from the previous one. Okay, so means an increment in the conductivity with rise in temperature, it gives the presence of NTCR phenomena for in all cases. But if you select the temperature range of 448 K to 298 K, then it will be demonstrating the PTCR behavior in all composition. Next. So these are the other compositions. So here we have given the real part of impedance with respect to the frequency. So here you can see that the real impedance factor value decreases by increasing the temperature in the lower frequency region. But at the higher frequency region, all curve will becomes merged, or it becomes almost similar value irrespective of the temperature. Okay, so this trend of spectrum may be cause of the release of space charges at those frequencies. Next. So similar type of a behavior we are getting for other 9 compositions. Here is the imaginary impedance with respect to the frequency. So here again you see that we are getting the relaxation procedure, which will be responsible for the existence of immobile electrons at the lower temperature and vacancies or defect at the higher temperature. So here again we get at the higher value of frequency, all curve will merge or give the almost constant value. So similar trend we are getting. This is another important dielectric property or the Nyquist plot of the material, where we'll get the semicircular arc. So here you see that at the lower range of temperature, this Nyquist diagram is not detected, where at the higher temperature, the occurrence of semicircular arc appear for the most of the composition, which give the single conduction process in the material. So we have given the simulated circuit diagram, also equivalent circuit model for representing this phenomena, and we have fitted the value with the red line. If you see in the curve, so it will be the fitting, and we use the Gypswin software for fitting those semicircular arcs. So we got the same trend for other composition also. This is the electrical modulus. So if you see that in this case, the m dash value has the maximum magnitude with specific frequency 10 as relaxation frequency. So at which this m dash maximized shifted toward the higher frequency region as the increase in the temperature. But at low frequency region, it value decreases slowly on rising the temperature, as well as the entire spectrum of the real electrical modulus approaches to zero with dispersion for all the samples. So this is the due to the occurrence of short range mobility carrier or the electrode or ionic polarization in the material. So same trend we are getting for another series component where we are getting the m dash values. This is again the m double dash or the imaginary value of the electrical modulus. So here you can see that at the lower frequency, the location of the peak shows the transition from the short range to the long range mobility carrier at which the ion may be free to travel longer distance. So this shifting tending of peak position toward the higher frequency propose the existence of the thermally activated relaxation process in the compound that denotes the charge in the hopping mechanism actually. So similar trend we are getting for the other values of lanthanum. So we are propose the imaginary modulus analysis. So now we come to the ferroelectric part. So here we studied the ferroelectric property of the material by using the P loop tracer. So here you see that there is we for all composition we are unable to get the saturated loop, because if you remember that in case of BFO, this bismuth is responsible for the polarization or the electrical polarization due to the 6s2 lone pair of the bismuth electrons. So here we'll got the different polarization curve, but are not very much saturated because we have some electric field restriction also, and we use the data at the room temperature only. So similar we are getting for other sample. Here 336 samples are there. Similar another samples, 3 samples is given in the next slide. So here we have given the all comparison. So for 0.10 to 0.90, what are the remnant polarization, what is the maximum field or the maximum polarization we have calculated. So if you compare that for a certain value of lanthanum, we got the maximum value, but others are the lesser one. So it may not be possible to achieve the properly saturated loop because if the applied field is beyond the breakdown voltage, then due to the leaky characteristic of the material also. And the remnant polarization and coercive field affected by the charge defect or the thermal treatment and the mechanical stress factors also. Okay, so there are due to some limitations we are unable to do that. But in case of magnetic property, again we studied the MH loop at the room temperature by applying the operating DC field of plus minus 20 QE. So here we get that room temperature, the coercive field and the magnetic remnants of the all composition, and which is found almost to be zero. And here we can say that the MH curve for the all composition displays a linear field dependence of magnetization. So here again we have given the MH loop for 6 samples. So remaining 3 may be on the another slides. And here we compare the value of magnetization, retentivity, and maximum field also. Okay. So it is noticed that due to these parameters, we can predict that these types of substitution or rare earth substitution are responsible for some application point of view. So if we are getting good magnetic property by substitution, so we can utilize those material for magnetic field sensors, and similarly some tuning device like oscillator, phase shifter, or filters as if they give the good electrical behavior as comparable to the pure BFO. So in summary, if I want to say that what we have studied by doing this 9 series of lanthanum doped sample, so the crystalline structure and the parameter were calculated using the Poudmar and by XRD profile, and the average crystalline size was found for all series between 30 to 53 nanometer. Then the elemental analysis confirmed the presence of all the elements which we have confirmed to the EDX. Then SEM confirmed the composition consists of the cubic and the spherical these grains and having the different dimension. and certain degree of porosity also. And this size, shape, and the nature of particle confirm the presence of polycrystalline nature in the material. Next. So here you can see that the temperature dependence of dielectric parameter we have studied, which gives the dielectric parameter increases gradually by growth in temperature for all operating frequencies. And then AC conductivity suggests that the dispersion at the low frequency region and the conductive value rises continuously with a rise in frequency. Then the variation in the conductivity value and their activation energy for all the frequencies are small at the lower range of temperature, and it tend the largest at the high temperature region. Okay, an increase in the conductivity, which mostly confirms the NTCR behavior or the semiconducting behavior in the material, except the certain range I have given in the slides, which confirm the PTCR nature also. Next. So here, the basics of the above detailed study demonstrate the electrical characteristic of alec substituted bismuth ferrite material owing to existence of multiple electroactive regions and their sensitivity changes in the thermal condition. And the impedance analysis plays a vital role in understanding the overall electrical behavior. Then P loop obtained at the room temperature approves the ferroelectric term of the all series compound. And the magnetic hysteresis spectrum loop, all the series compound can be observed that the MH loop of the synthesized sample exhibit the higher saturation magnetization value at the field plus minus 20 ke at room temperature. So on the basis of above studies, we can conclude that there are several possibilities to achieve the room temperature this multiferric material with a suitable choice of components. So I am thankful to SERB for giving the research project EMR, and these are the some publication which is based on this study. And I am thankful for my research scholar Nipesh, due to which I getting lot of data. And I am thankful to my collaborators also at IIT Guwahati and IIT Kharagpur for availing the certain lab facilities there. So thank you very much for your kind attention. Thank you. Hello.
Thank you very much, sir.
Sir, again internet is fluctuating here. Hello.
Okay. Yes. Thank you very much, sir, for your today's invited talk. If anybody have any questions, please raise your hands in the chat box.
And sir, if possible, they can send it through email also if they have doubt, because
Yes.
I am not hearing your voice properly also.
Okay. Fine,
Okay,
sir.
So, thank you, sir.
So, on behalf of Gondwana University, Gadchiroli, I am indebted and thankful to Professor Alok Shukla for sparing his valuable time and presenting a nice presentation over here. Now, we shall move on to the next technical session. For this technical session, we have Dr. S.B. Revatkar, Dean, Science and Faculty of Science and Technology, Gondwana University, Gadchiroli, here to chair this session. There is a little bit change in the chairmanship due to unavailability of Professor F.C. Raghuvanshi. Dr. Revatkar sir will chair this session.
सर शेयर कंटेंट शेयर स्टार्ट कर दीजिए प्लीज.
Yes, sir. So before proceeding,
हाँ शेयरिंग स्टार्ट कर दो मैंने. Then I will upload my file.
Yes, sir. We shall do this. So before proceeding, I will. It is my pleasure to introduce Dr. Revatkar. He is Dean of our Gondwana University, Gadchiroli. To his credit, 52 publications are there in the journals of international and national repute. He has successfully guided 5 PhD students under him. And so this is a brief biodata of Professor Revatkar. Now I request our Dean and Professor Revatkar to chair this session. Please, sir.
Good morning, sir. Professor, good morning.
Good morning,
Hello.
sir. Good morning.
Good morning.
Good morning, sir. आवाज
Good
येते ना
morning,
सर?
all the friends. आवाज येत आहे. Good morning, all the friends.
Okay, thank you.
Now I introduce today's speaker, Dr. H.J. Dhobre, sir. He is my best friend. Professor Sanjay Dhobre obtained his MSc degree in physics from Rani Durgavati University, Jabalpur in 1988. He obtained his PhD degree in 1992 in solid state physics from Nagpur University. Dr. Dhobre is presently working as a professor in Department of Physics, Rashtrasanta Tukadoji Maharaj Nagpur University, Nagpur. Dr. Dhobre stands among the top 2% scientists in the world in the prestigious list published by a team of scientists in US Stanford University in one of the highly rated journal, PLOS Biology. During his research career, he has worked on the synthetic and characterization of solid-state lighting material and phosphorus for solar cell efficiency enhancement, as well as development of radiation dosimetry phosphor using thermolysis technique and utilization of flash ash. Dr. Dhobde published 35 patents and few of them are already patented. More than 629 research papers are published in Scopus Index journals, and his H index is 32 and has 6,329 citations on Scopus. Dhobre's citation on Google Scholar is 8,193 and H index is 37 and I-10 index is 228. Dr. Dhobde successfully guided 61 students for PhD degree. He also edited and authored 15 international books. Dr. Dhobde is an editor of Luminescence, the Journal of Biological and Chemical Luminescence, John Wiley and Sons Limited publication. He is also a recipient of India's Top Faculty Research Award 2018 by Careers 360 for the top 10 researchers in India in physics on the basis of the research papers published in Scopus Research Database in the session 2017-18 on 20th March 2018. He is also Fellow of Maharashtra Academic and Sciences and Fellow of Luminescence Society of India. His ORCID ID 0000 0002 4249 8228. Now, his today's topic is color rare earth activated phosphorus for solid state lighting. On behalf of Gondwana University, I welcome Dr. Dhobde sir. Thank you. Dhobde sir.
Thank you, sir. Dean of Science Faculty, Dr. Suresh Revatkar, sir, for your kind words for me. And I'm very much thankful to Vice Chancellor, sir, Pro Vice Chancellor, sir, and ex-registrar Morley, sir, and all team of organization committee. Today I'm discuss on the one of the best topic in the field of the luminescence, color tunable rare earth activated phosphor for solid state lighting. So this topic is interesting due to the very low energy required for the lighting and how to enhance the luminescence intensity by different way. It is contained in terms of the color tunable. And rare earth ion always exhibit the luminescence in the host material. So particular type of the host material is emit show this type of the property, and that rare earth ion just like a europium, dy, tb, ce, all these material are very interesting in the field of the luminescence. So this is my university accredited by A grade. Try to discuss it very briefly on luminescence, then white light generation, importance of inorganic phosphor, how to enhance the luminescence intensity, and color tuning the color by different way, luminescence in lengthened ion, thermal stability of the light emitting phosphor. It is also important, and application. So I will try to cover within the time allotted to me, only 40 minutes. So I will try to complete up to the 12:30. This is my talk. So just so you can see, the luminescence is the phenomena in which substance absorbs the energy in one form and re-emit the fraction of its or as visible or near visible radiation. That means any material you can exposed by high energy radiation. It is not necessary the all radiation absorbed by this material, but some of the energy absorbed by this material, it is a characteristic of this material. And after that, during some process, this material emit the light. But this emission of the light is totally depending on the activator present in this material. And this activator is find the proper symmetry in the lattice, so that emit the very proper way. So just you can see this is the process of the luminescence. Just the N1 equal to the ground state, and you can excite it by this by external energy electrons. Then this energy h mu absorbed by this electron in the ground state and is excited, and again reach at the high energy level n equal to 2. But this electron in the excited state is not possible to stay at the higher energy level for the long time. So that again jump to the lower energy level, and then during this jump from n equal to 2 to n equal to lower energy level, so this is the emission of this electron or this energy photon, it is called the luminescence. But sometimes this electron absorbs the more energy just in the present the n equal to 1 lower energy state, and absorb the more energy. Then it is also jump from n equal to 1 to higher energy level n equal to 3. So in that case also this electron jump in the lower energy level, and this is called the initial transition. So during this downward arrow, during this process, emission of the photon in terms of the light, and then emission of this photon, it is called the luminescence. This is a very simple way to presentation of the luminescence. But luminescence is a very broad area, and its application in the different fields, just the lamp, laser, display, TLD, LED, ink, dating, TV, and so many areas. Just we can exhibit here, and main some of the forensic and of conversion are very interesting in this case. So if anyone is working in this particular one field, then it is more than sufficient. So it has so many materials, good characterization, and then it is useful for this way. So just you can see the roadmap of the lighting, and just consider the whole roadmap is from the fire kerosene based oil to again up to the LED. So this everyone is the generation. It has some problem, and this problem faced by scientists, and remove this is the problem, and this new generation of lighting is observed. So all this is converted in the fourth generation. This is the fourth generation. This is the only for the lighting and kerosene based lighting. But it has some drawback. It is a very harmful, very dangerous gases emit from this kerosene-based lighting. So it is not the eco-friendly. But nowadays, any research work is in progressive stage that is requires a low-cost, eco-friendly, and is useful for the society. So this kerosene-based lighting, it is not the eco-friendly. So it is a cancel. Again, some modification here. So next generation lighting, it is a tungsten filament lamp. But this tungsten filament lamp is the lifetime is the 1,000 hours, but it is a generated heat. So in the room, some present the oxygen, it is also converted into carbon dioxide. And within the 1,000 years, this is a tungsten filament lamp emit the half ton of the carbon dioxide, and heat also generated. So this is also consume the more electric power. So this lighting also the fail in terms of the eco-friendly. So again, some work is going on, and the next generation lighting is also the fluorescence-based lighting. In this fluorescence-based lighting, inside the some mercury, and RGB means red, green, blue phosphor coated on this inside the tube. And just when switch on, then this mercury is converted in the vapor form, and emission is the 285 nanometer is the 251 nanometer. 85% is the converted in this 251 nanometer, and remaining 50% is the other wavelength. So this material coating inside, so it is a completely absorb this energy and converted in the red blue green light, and combined you can observe the white light. But it has contained the 40 milligram of the mercury in the fluorescence tube. So after the disposal of this fluorescence tube, it is this mercury spread in the open atmosphere, and so many environmental problem is generated. But in the same time, it is modified by the compact fluorescence lamp. But it is also operated by the mercury, and but it is the quantity of the mercury, it is less. So it is a very cool light. It is 75% electric saving, and this is the fluorescence CFL. It is a 10,000 hours. It is a lifetime. So, but it is also operated by the mercury. It is not the 40 milligram. It is the 4 milligram. But again, as per the scientific nature, this also it is a very harmful. That again, CFL it is a fail in terms of the eco-friendly. After that, the light emitting diode is the best technique for the artificial lighting, and it is a completely mercury free, and it is the lifetime is the 1 lakh hours. But again, this light emitting diode is it is a consume the very less energy, and 90% electric power is saving, and it is a very long life. So on this term, this is very useful in terms of the environmental problem. It is also very useful, available in the different color and size, shape and size. Also, it is a cost is much not much more, and it is consumed very less electricity. So this is the LED lighting. It is a nowadays it is very popular, and I'm just discussing which type of the material available suitable for the LED based lighting. So this is the LED based lighting. It is completely replaced by the CFN, and this is just to see the diode. This diode it is useful for the purpose, and but we are trying to develop the different type of the material for this diode. And here, just you can see here the advantage of the LED lighting: 1 lakh hours, no moving part, 5 minutes is the diameter, 90% less electric power, and variety of the colors. So this is the best of the one. So what is the application of the LED lighting? LED lighting useful for the street and house lighting. It is indoor plant cultivations, indicators and display, as biomedical application and data communication and signal transmission. So all this is called the Li-Fi. So all this type of the again so many application of the LED. I'm just containing some of the few of the application of this here, but so many application possible for the LED based light, only depending on the which wavelength emitted by the light. So this is the application are very drastic from the normal place to the defense to industry and medical sciences also. So this LED luminescence and LED based lighting is important for the research and nowadays also. So it is directly related to the energy saving material. Again, indoor and outdoor lighting, full spectrum lighting, near infrared lighting, plant lighting, laser lighting, and high power lighting. So all this type of the lighting possible with help of the LED, and this is all called the artificial lighting. But how to emit the white color? So just we know that the red, blue, green is combinedly emit the white color. But nowadays the two color LED also available in the market only for the blue and yellow color. So this blue and yellow it is also combinedly emit the white color. Which means you can excited by the UV light and then emission of the red, blue, green, then possibility to the white light emission. So this is the best way to emit the white light. But for this purpose, just you require the blue color, green color phosphor, and red color phosphor, or yellow and blue color phosphor. So for this purpose, just we can work on the how to develop the different color emitting phosphor for the white line emission. So this is the completely indicated to here. Just the blue and yellow for the white light emission, UV chip for the excitation purpose, and then RGB. It is also possible the white color, blue chip and red and yellow color. It is also combined with the white color, and this blue chip red and green also possible to the white color. So this is the way of the emission of the white color from the LED. So now just for this purpose, this is the different type of the ions are very useful for the host material, and but it's the activator. So this is the rare earth is very important. So in this mainly periodic table, this is the rare earth row is very important for the application for the phosphor. Just you can see here the LACE, PR, ND, PM, SMU, GD, TB, DY, HO, TM, YB, and LU. But all this rare earth characterization is not possible to discuss to here. And some of the rare earth I just discussed, and maximum I will concentrate on the European. So this is the very good material for the one. So in this my presentation, I'm just European, C, DY, TB, and SM. All this type of the iron very useful for the emission of the light, and this emission of light just indicate to here. Uh, just now I'm just concentrate on the synthesis methods and characterization of the rare earth activated LED phosphor. So if any type of the field, just the main part is the how to synthesize the material, and if you can discuss the synthesis of the material by a very low cost technique or very easy way, so this is very useful for the industry purpose. So my concentration only for the synthesis of material by a different way. So for this purpose, I'm using the aluminate, borate, chloride, nitride, oxide, phosphate, sulfate, sulfite, titanate, tungstate, vanadate, and silicate. All type of the host material. It is a single, double, or triple type of this. I'm working simultaneously all type of the host material and just use DYCV just as per the earlier. All this activator for this purpose. So now some of the experimental method. So the solid state wet chemical and novel synthesis. Solid state in this melting and the solid state diffusion. These are both are the very popular technique. Wet chemical is the co-precipitation and novel is the combustion and solid method. So all these methods are very useful for the preparation of the material. This is the one of the technique is the combustion technique. Just you can see here. One of the condition in the combustion technique, all starting material in the nitride based phosphor. Nitride based material is as a starting material, and just you can mix in the stoichiometric ratio, and then just you can find out the one gel. And this gel put in the furnace at the 550 degrees centigrade. Just you can indicate in the figure. So this temperature of this furnace is the very less. But during this combustion process, just in the this one is the box. Just you can see here, this is the flame. Flame is of about 13 seconds only, but its temperature is the 15 to 1600 degrees centigrade. So this is the very well, in terms of the electric power. So furnace temperature is 550 degrees centigrade, but material is prepared at the high temperature 15 to 1600 degrees centigrade. This is the novelty of this combustion synthesis, and then this powder is useful for the next application. And this flame just you can observe, just to see here is for the 13 seconds, and then it is very useful for the combustion synthesis for preparation of the different type of the phosphor. And here you use the urea as one of the fuel. So this urea is the commonly used, but you can change the fuel that corresponds to the morphology of this material. It is also changes. Just you can see here, this is the material and after the combustion synthesis. And just this is the table. You can see the different type of the formula of this fuel. You can change the fuel during the combustion process. So morphology of this material changes. And if the morphology is the changes, then physical and property of the material it is also changes according to the. This is useful for the very good application of the in field of the luminescence. So now is the next is the soldier combustion synthesis. Soldier combustion is all material starting material is the nitride base dissolving the double distilled water, and this is the European is not rare, is not available maximum in the nitrate form, but its quantity is very less. So oxide material is also useful, but this is the first you can dissolve in the HNO3, and then you can make. And here it is a tetraethoxy orthosilicate, just in the dissolve in the ethanol and double distilled water. So then stirring in the 1 to 1.2 and 2:4 ratio, and then add the ammonia. So gel is formed, and then again is the same is the combustion process, and this is possible to the 550 degrees centigrade of the furnace, and then it is the material is prepared, and this material you can sinter at the high temperature up to the 1300 degrees centigrade. So silicate is required. The quenching temperature is very high. So here it is the material is show a rare earth actuator show the very high intensity. So this is the requirement of this one. So by soldier method, it is maximum possible is a nanomaterial, and now nanomaterial is the best way to exhibit the application. Now this is the next is the solid state diffusion technique. It is a very rough technique. It is the oxide material with the urea. I'm sorry, ammonium dioxide and phosphate you can mix, and then in the stoichiometric ratio, this is the prepare the AlPO4. So this is the first you can crush it for 1 hour, then properly diffusion of the all starting material, After that, you fire at the 500 degrees centigrade for 2 hours, and then again you can remove this material from the furnace, it's slow cool, and again you can crush it for 1 hour. So during this crushing, the diffusion process is very important part, and then it is possible the again to higher fire at the 1000 degrees centigrade for a long time, just like a 24 hours. So at this high temperature, this diffusion is very important, and this properly diffusion process, this material is prepared, and this is very useful. But from this method, micron size material are possible, nanomaterial material is not possible. So now the simple and very powerful technique is the wet chemical synthesis. It has only for the starting material in the nitrate form. You can dissolve in the double distilled water, mix with the rare earth ion, and then rare earth ion dissolve in the HNO3. And again, just you can heat at the very low temperature, by a very critical temperature, 60 to 80 degrees centigrade for the long time, up to the it's converted in the final form. So by this technique is the Na2SO2PL2PO4F9. This type of very complicated compound is prepared, and this method is very low cost. It requires only for the borosilicate beaker, and it is a rare earth, very small quantity, and just higher at the 70 to 80 degrees centigrade, a simple one is possible. So some of the colleges, it has not the good facility for the preparation of the material. So this wet chemical synthesis is possible at the college level also. So if newcomer start the research, so this wet chemical technique is important for emission of the light, and this is the emission of light is preparation of this material. So this wet chemical technique is one of the technique for the preparation of these materials. So this is the very low cost technique. Now it is the prepared material you can characterize by the XRD for the confirmation of the material. And if this our material is the lines or data is well matched with the standard data available in form of the JCPDS or ICDT. So JCPDS, it is the new name is the ICDT, you can match, and if it is the well matched, then it is possible. If you are expert, then ritual, it is also possible. And then if the ritual is the depend on the factor, and if this with help of the ritual, again you can confirm the structure of this material. So this is the XRD data is very useful for the material characterization. Then same technique and same technique, it is the morphology of this material is possible. EDX, this is the what is the concentration of this material. FTR is the which type of bonding in this material. It is also confirmed with the FTIR. And then as a luminescence property by the photoluminescence one, then it is spectrofluorometer. This device is possible for this photoluminescence study. And UI parameter or other parameter, Dexter technique study, theoretical study, all are the theoretical parameter is study for the full characterization of this material. So all these characterization are required for the luminescence material. Now this is the X-ray diffraction math unit. This is the photoluminescence for the spectrofluorometer. This is the two unit are very possible. Now I'm trying to just discuss some of the material synthesis to here. This is the Ca1 minus X Zr4 PO4 whole 6, and this is the rare earth ion. Just we are trying to the europium SM and PR3 plus ion. So just you can see here that this is the prepared by the solid state diffusion technique. Then in the stoichiometric ratio of the calcium carbonate, Zr oxide, ammonium phosphate, and europium oxide. So this is a heating at the 2 hours at the 450 degrees centigrade. Again slow cool, again crush it for 1 hour. So for the proper diffusion, and again fire at the 800 degrees centigrade. Subsequently, then this material is the prepared, and it is the XRD which well matched with the JCPDS file. This is the morphology of this material, is the micron size of the material are prepared, and this is the excitation is possible 96 nanometer and 467 nanometer. So in the fluorescence tube and CFL is required the excitation of the mercury. It is the emission the 254 nanometer, but it is very harmful. But LED is the required aluminum gallium nitride is particularly in the composition, and emission is possible near UV means 396 nanometer. So this emission is very useful for the LED application. But if the sometime is the 467, it is a blue excitation. So this is so many material available in the blue excitation. So this is the source of the excitation in the LED material. Then you can cover some emitting phosphor on this material. So white light of emission is possible. So for this material, the monitor is a 615 nanometer. So you can see here the two emission line are observed. One is the 591. It is the intensity is very less, and second is 615 nanometer. it is a 5D02 7F2 transition, and the 591, it is the orange color, but it is the intensity is less, and it is also varying with the concentration of the impurity at the 396 nanometer. So maximum intensity observed here is the 4 mole percent. So this is called the concentration quenching of this material. Now you can see here another material. It is the and this is the SM3 plus. It is the and monitor is the 598 nanometer. So just is the emission is of the 598 nanometer due to the 4G5/2 to 6H7/2 transition. And this emission, it is also orange color for the white color possibility. And third one is the PR3, same host. The PR3 plus is the excitation the 446 nanometer, and then emission is observed at the 485 nanometer, and 485 nanometer is directly in the blue colors. So all these three colors with the same host PR, SR, SM or EU is very useful for the white color emission. So this is the 485 nanometer is the emission of the PR3 plus with the different concentration. And just you can see here Indian gallium nitride with the gallium 1 minus X, and then vary the X value. So X value is the 0.022, then 460 nanometer emission, X is the 0.13, then 405 nanometer, X equal to 0.09, then emission is 395. So depend on the X value, it is a different type of the emission is possible, and that this is a very good excitation material. Now see the U3 plus is the 395 nanometers and rare emission. This is called the again host material. Just you can see here, this is the structure of the same host material. Now here is the emission is the SM 598 nanometers, the orange emission, and in the third one it is the emission actuator is the PR, and then blue excitation, then PR blue emission is possible to here. Then all this material is show the white color. So by this way, just Indian gallium nitride is particular type of the composition for different material, and you can just observe that this is a very good emission possible. And this is also indicated in the CI diagram. And if this curve in the triangle, so it is much more supported to the white color, and then it is the possible. It is one of the characterization. So sulfates maximum use the illuminate in this LED application, silicate also, and other is the very small sulfates and borate, bromide. So as per your requirement, you can select the particular type of host material with the different actuator ion. So now U2 plus emission is the very broad, and U3 plus very sharp emission. But U2 plus, it is not always show the blue emission. It is also U emission, blue emission, ultraviolet in the emission also, blue emission also, green emission also, red emission also, and white light emission also. So only one activator also show the white light emission in the different host light lattice. This is the beauty of this compound. Just the European dope in the RB BASC Si3 plus. This is the amorphous metal complex method. Just you can show here is the emission, and that is the this is the ritual of this one. So with help of the ritual is the chi factor is the control way, and then you can observe the structure of this material, and it is the morphology shows the very micron size of the material. Now, in this case, the FTR, it does not show the any OH molecule, and if the OH molecule is present, then this is the kill the luminescence. Other and if the free of OH, then it is show the good luminescence. And this FTR is show the SiO bonding. It is also show the SiO bond, and is the SiO is the bending vibration. All type of the bonding show the by this FTR one. So now this is the emission is observed 492 nanometer at the 365 nanometer. So this emission of this one material is a cyan color, and is the decay is also nanoscale region. So these two characteristics it is supported one, and then you can show that this is the variation of the European concentration. So maximum intensity of the for the 2 mole percent. This is called the concentration quenching. So all these parameters show this material the very good emission the 492 nanometer. This is the LED fabricated by this material. This in cyan color work. So this is the very good output, and this work is published in the Journal of Allied Compound, and its impact factor is the 4.65 nanometer. So this is the very good quality of the work. So this is the shows the CI diagram, and then this is the LED one. And other factor also jobbing on Rex method is also study some thermal stability. Thermal stability also requires this material at the room temperature to 150 only for the slightly intensity is decreasing. So this thermal stability also one important, and other parameter it is also possible for the publishing the good paper is the high impact factor. So now another work I'm just discussed to here, Ca2Mg Si2O7U2 plus is the, and this European 2 plus show the green emitting phosphor. Again, this is work done by the Namita Brahme and DP Beeson group. So this is the prepared by the solid state diffusion technique, and this is the study is matched, will match with this one, and this is a nanomaterial material prepared by the nanomaterial. So this is a very good material. And just you can see the after the 329 nanometer, the excitation emission is observed of the European the 530 nanometer, but it's a very broad peak. And this broad peak only possible by the European 2 plus I. So this European 2 plus also show the good luminescence, and it is a point it is observed in the CI diagram in the triangle. It is supported to the white light emission. And just you can compare with the ML study also, the same ML emission it is also observed. This is very good compare, well matched with the photoluminescence and macroluminescence study also. So this is the great result in the field of the luminescence by the Raipur group. And now next material, it is the SR2, SR5 and 8U2 plus, and this is the red emitting phosphor. It is prepared by the abroad centrifugal and reported in the chemical materials. So just you can see here, the excitation, there's a 450 nanometer or emission, excitation is 340 nanometer. Emission peak is the same position, is the 618 nanometer. But this the two peak of excitation is observed. One is here and second is the here. But in the both case, but here the same point. So 14 nanometer excitation intensity slightly is the higher. So and next one again compound, I'm just discuss the BASR-MG pure twice. This is also published in the General Alloy compound in the 2010. So this compound show the white light emission. This is the very beauty of in the field of the our field. So now just you can see here, excitation is the 350 nanometer, emission is the 447 nanometer, 536 nanometer. So this peak start from the visible region for 400 nanometer to directly 700 nanometers. So all spectrum is covered. So this is the white light emission is possible. And if this type of the result is possible, so there is no require the other material. Only for the one material and one activator show the white light emission. So this is the highly quality result in the field of the LED or luminescence. So this is the challenges for the newcomer of the students to work hard and try to develop this type of the material, and excitation is the 350 near to a UV result. So it is also very supported to the LED light. So all this type of the work is possible. Now a very big question. Okay, you can develop the emission in the particular level. My topic is the color tunable luminescence. So how to enhance the luminescence intensity of phosphor? So this is a very big question. So I'm just tried the enhance the luminescence intensity is possible by the number of the way. One is the, this is very important for the newcomer student in the research scholar in the field of the luminescence. Number of combination of the excitation emission wavelength. We'll try the different type of the excitation, different type of the emission is possible. Where is the maximum intensity by particular excitation you can find, and this optimization excitation is very useful, but it is totally depend on the nature of the activator. Now is the chemical root synthesis. Same material you can prepare by the different chemical root synthesis, different starting material, and just you can find out the which starting material or which chemical root technique is best for the high intensity. This is also enhance the luminescence intensity. Third is the starting material. You can change the starting material. Sometimes you can use carbonate, oxide, nitrate. So it is also change the result also. And a heat treatment. Heat treatment is when you can prepare material according the different temperature, then sometimes particular type of the phase is responsible for the high luminescence intensity. So you can also find out. So by this way, you can try to enhance the luminescence intensity. But only not this 4 point. Other way also source of light, that is the activator, sensitizer, and host material also means color tuning. So you can change the activator, it is also possible. You can change the sensitizer, it is also possible, or you can change the host material. So this is also possible. So this study is nowadays is a very big demand for the color tunable. And so just you can see here, a particular approach of the color tuning, control the doping level of the activator. So activator concentration you can vary due to the concentration you can find out the particular one position. After that, the activator is the same position. You can change the sensitizer. Again, you can find the optimum concentration. It is also useful. But combination emission of the host material like the tungsten, molybdenum, vanadate, all this is the self-emitting material. So this is also possible. But sometimes you can replace the VO4 by the PO3 MO4, VOW4 or PO4. So then emission intensity also possible to the change. That means you can change the host material, and you can changing the host material intensity and peak position of this material is the changes. It is called the color tuning. So this color photoluminescence shifting also you can call this very common language. So this is the very important. So this is the possible by the cation substitution. This is also possible by the anion substitution, and this is also possible on the cation and anion substitution also. That means it is not necessary you can replace by the CaBmn also only by the double ion, but you can also possible in the MO4, UO4, AWO4, it is also changes. So or both are simultaneously changes, then this is a good result of the last 3 years. I was published so many paper in this the color tuning phosphor, and this is a very important and a good impact factor for this good for this result. So I'm just some of the points is discussed here. Controlling the doping level of the activator ion. Yes, you can see here. This is the host lattice. Is the symbol of the green. It is the host cation. Other this is the brown color. It is the anion. This is the anion, and this is the blue. It is the activator, and red it is the activator. But this is a small radii. So if this host lattice you can replace by the activator, and it is the radius is higher as compared to the host lattice. So this is the create the stress. So it is the blue shift is observed. But suppose you can use the rather different type of the activator. It is the radius is less as compared to the host lattices. So this is the stress observed in the activator, and this is the red shift. It is also observed. So this is the main point of the main mechanism of the red shift of the blue shift, or it is also called the photoluminescence shifting for the MSc student. This is the good point. And again, with help of the, you can change the particular host, and according to the radius of the activator and host, like you can analysis. So this shifting is possible, and this is called the color tunable shifting. So now recently the Hug and et al. Reported the this LICA3 MG VO304, and this is the European 3 plus, and it is just tried to the replace the VO4 by the European, and then you can see here the VO4 group, it is a self-emitting group, and you can change the European ion. So excitation is the 336 nanometer. By increase the European concentration, tunable bluish color is it is also observed. Just you can see here, this is the 366 nanometer excitation. This peak is observed 490 nanometer. So here is the three type of the peak is observed. This is the one 470 nanometer, 546 nanometer, and then this is the different type of the color emission is possible. Now this energy transfer from the VO43 to U3 plus, and this VO4 energy transfer directly U3 plus. So this is the 612 nanometer emission as another wavelength. It is also energy is the transfer in this host material. But and here you can see the different type of the excitation 336, 612 nanometer emission is possible to see here. And if the again if the emission is of the 490 nanometer. So all this out of this is the 612 nanometer exactly the red color of the spectrum. So this is the by changing this one emission intensity is the drastically is the changes. So other part, just you can see the concentration changing that 0.4% intensity is higher, more than 10 times. Then you can find out the different concentration of this color. Here is the saturation is observed, and that this is the optimization of this concentration is more important for this one. So again, you can see that this is the color is shifted from this one 1 to 12, and this is the white light emission 9 to 10 point is very important, very close to the white light. So another example is the calcium GDWO4 whole 4. Here the two activator I am trying to discuss, TB3 plus and U3 plus. So here it is 380 nanometer, so green to yellow and orange, and finally it is a pure color is observed. So here you can see in this region. So particular type of this material you can excite by 380 nanometer, then emission is observed by 45 nanometer of the TB3 plus ion. So this is the green emission. But same material, you can use the Europe 3 plus is the 395 nanometer, and emission observed is the 616 nanometer. So upper color is the green one, below is the European 3 plus by the red one, and by particular excitation, and simultaneously both are you can dope it. So 545 nanometer peak intensity is the decreasing, but 616 nanometer intensity of U3 plus is the increasing. Just you can see here, This is the 618 nanometer peak is increasing with the changing the TB3 plus ion. So this is the European to TB3 plus. This is the energy transfer, and it is called the green to red color emission is possible. Calcium gadolinium tungstate material with the TB and U3 plus. That U3 plus emission in us with help of the TB3 plus. Then energy transfer we are considered TB3 plus to the U3 plus. But this is also possible to via the tungsten ion. Then tungsten it is also emit one of the material. So this is the TB to U3 plus. This is the energy transfer, and then this is the it's called the color tunable phosphor. So now in this the one of the compound, this is the BAM is the U2 plus is the well-known compound. This is the prepared compound BASRSI, and this compound then completely emit the white color. So all this is are very required for the emission of the color. So now varying the concentration of the sensitizer actuator. This is also very important mechanism for the emission of this material. Just you can see and directly jump off this result. In this, the TB3 plus ion excitation 400 nanometer, then 480 nanometer is 45 nanometer emission, and this emission directly is the green color of the spectrum. But you can dope the U3 plus, so TB3 plus ion intensity more in us. So again, this is the same type of the energy transfer mechanism is observed. So C3 plus you can dope, then C2 TB3 plus and TB3 plus to the U3 plus. So any material, it is the emission is well matched to the excitation of the other activator. So then this energy transfer from the excitation, emission of the one activator to excitation to the another material, and then again this is the this energy is transferred to C to TB, TB to U3 plus, and here it is the luminescence intensity enhanced. So this is a very good way to the development of the phosphor for the white light emission. So all this now is the cation substitution. This is very interesting in this my presentation. And just I'm not going in the detail. Just you can see here the particular type of the material by cation. This is the blue color peak is the decreasing, and the other color it is actually increasing. So this is a variation of this the two ion. So anion substitution, just you can see here, MO4, WO4, PO4, and VO4, all you can replace to each other in the particular type of the force. That this is the emission is shifting is possible, and this mechanism is the main part of this my study. Just in this compound, just one of the compounds, the KBIPMO4. So this MO4, it is also possible you can replace. So MO4 here is the U3 plus concentration is the vary, that emission you can observe 650 nanometer after the 395 nanometer. So red color of the emission is possible. So excitation is the 395 nanometer. So emission is the 650 nanometer. This is one of the way why the concentration can change. But in the same material, just this the MO4 you can replace by the WO4. So this WO4 it is the value of the Y. It is a 0.2, 0.4, 0.6, 0.8, and 1. That corresponding this is the intensity is the drastically is the changes. So this is the increasing the intensity of this emission by you can replace by the MO4 to WO4. So this is called the color tuning by this energy. Just you can see here. So this X value is the vary. So this is initially X is equal to 0, X equal to point this value. So this peak is the developed, but this is the same peak intensity here. So particular type of the concentration of BO3, this is the two peak are observed. So that means one material, PO4 you can replace by that BO3 in the SR5 the PO4 whole thrice Cl hello phosphate by the U2 plus. So this is the 550 green emission is phosphorus. Then in the same material, blue emission and green emission both are observed. So this is called the novel result. Sometimes you can submit the paper or some of the high impact factor. So just editor or referee shows what is the high novelty in this your material. So this is the novelty of this material. If this type of the result are possible, so this is the best result in your field. So this is a very nice way of the presentation. And again, some of the this blue color is the increasing, then again red of this one is the decreasing. So by this value. So I'm not going in the detail. Our chairman it is directly see to me how to control your talk, and this is also laughing also. Okay, good sir. So this is the dean of the Gondwana University. It is a good power and good researcher. So now one of the example of the SR5 PO4 whole thrice act. It is C emission in U2 plus. So in this material C2 U2 plus. Just I'm one of the example is the just discussed to here. Excitation is 354 nanometer of U2 plus and emission 440 nanometer. But I'm trying to the same material is the C3 plus. So 254 and emission is a 355. So emission of the C3 plus 355, it is a well match to the U2 plus excitation 354. So then this intensity is enhanced. How much enhanced? By the 10 times. So this is the one material excitation is well matched to the emission of the other one. So intensity is the observed by the 10 times. This is called the energy transfer. So this funda is very useful for the color tuning of this material. Why? Due to the overlapping of these two curves. This is the one material excitation. It is the second emission is the well match. So this portion, it is responsible for the emission of this light. So and this is the again one of the paper. This is myself, BA PO4. So I'm just trying to discuss to here. BA you can replace by the MG. So my time is I think over. I'm directly show that the last very interesting graph, and then with help of the graphical abstract, you can it is very clear. And then I can stop my presentation. Just 1 minute. Yeah, this one. Just you can see here. Initially, your compound is the BA2 Mg PO4 twice U2 plus. But here you can replace by the PO4 by BO3 4. So it is a quantity of the 0.2, 0.5, 0.7, 0.1, 1.2, 1.5. So this is the color of the blue. It is the directly is the changes, and this blue emission peak is the stop, and again another peak is developed. So after the excitation of the three line. So how to write your result in the particular one graph? This is called the graphical abstract. This graphical abstract represents the whole paper. So this is the quality of my group, and this is the paper recently published in the Journal of Allied and Compound by the Sumedha and Govind Nair. Govind Nair, it is the presently working. So I think, Chairman sir, I will drop the some of the stop here. And this is a very good material for the possible work in the future. If anybody interested to collaborate with me, my lab is always open. I'm working in the high good field that this is a very good material for the working. So my research area is the synthesis and characterization of LED material, development of the radiation tolerant phosphor, photosynthetic phosphor, utilization of the flash, water purification, and fabrication and development of the luminescence device. So this is my group and my collaborator. So without collaborator and without research, research is not possible. So I'm very thankful to all my this research collaborator and research team. So this is the strength of my research. So I'm very thankful to all my research collaborators. So big thanks to all my research students and collaborators. And thank you very much. So if any question, then you can send the queries on my email ID at redditmail.com or gmail.com also, and this is my email ID. And I think my talk is complete within the 40 minutes, and I obey speaker for this conference. Thank you very much. Thank you, sir.
Dr. Dobre sir for his excellent talk on luminescence synthesis of rare earth activated characteristics of material, applications of luminescence, luminescence in intensity, color tuning, energy transfer, all these factors he has explained nicely. I am
Thank you,
thankful
sir.
to Dr. Dobre. Thank you.
Thank you, sir. Thank you very much for inviting me.
Thank you.
Eh, everyone. Okay. Bye-bye.
Today, for the second session, Dr. Mishra is about to join. So we shall wait for him. So he'll be joining within 5 minutes. So we shall wait for him.
You can hear me? Hello.
Yes, sir. Yes, sir. We can hear you.
Okay. I'm sharing the screen.
Revatkar sir.
How?
Mishra sir had joined, so we can continue now.
I welcome Dr. Mishra sir. I introduce now Dr. Mishra. He is the scientific officer in Department of Atomic Energy, Kolkata, West Bengal. He did his BTech Electronics and Telecommunication Engineering from Pune in 2002. Further, PhD Engineering from Mumbai in 2016. Uh, he is recipient of various prestigious awards. uh, Department of Group Achievement Award, Department of Atomic Energy 2009, Group Achievement Award, Department of Atomic Energy 2010, Group Achievement Award, Department of Atomic Energy 2017, Best Paper Award, IEEE Applied Electromagnetic Conference 2017, Best History Award 2018, IEEE Quiz Competition Award 2020. He has huge research experience. He has huge research experience. Variable Energy Cyclone Center as a scientific officer, Department of Atomic Energy. Highly charged ion beam development using ECR ion source for superconducting cyclone. Installation commissioning of indigenously built ECR ion sources for K-130 cyclone, development of high current proton source for accelerator driven subcritical system, design and development of radio frequency ion beam bunching system for cyclotron, development of beam instrumentation for high energy particle accelerator, development of RF amplifier, RF power meters, low level RF systems for particle accelerators, development of low noise cryogenic high frequency amplifier for pinning and tap, development of data acquisition hardware and data analysis software for particle accelerators, development of data acquisition hardware and data analysis software for particle accelerators, FEM simulations for RF cavities, superconducting magnet, beam peak for particle accelerators. His teaching experience. So he was the training program for engineering students in 2008. Further lecturer in analog electronics, beam instrumentation and diagnostic in 2012. Further, he was the MTech supervisor in 2014 and 15. Further, he has the great skill in the following fields: ion source, particle accelerators, MATLAB, Python, nuclear electronics, plasma, microwave engineering, cyclotron, vacuum, EHFSS, beam instrumentation, ion optics, RF engineering, microwave, waveguides, electromagnetics, antennas and propagation, antenna engineering, electromagnetic engineering, microwave filters, computation, electromagnetic, CAE, CFD, electromagnetic analysis, RF circuit simulations, CST, RF programmation, UWB, RF electronics, propagation, microwave technology, ADS, metamaterial, EMC, EMI, signal integrity, electromagnetics compatibility, RF technology, microwave communication, filters, radio propagations, electronics and communication engineering, radio engineering. So such type of skill, he has the great skill in all this field. He published the number of research papers in various international journals. Such great personality today we have. I welcome Dr. Mishra sir for his valuable talk. Dr. Mishra sir.
Yeah, thank you, and good afternoon to all the panelists and attendees. So, without wasting any further time, we will directly proceed with the presentation. Just I am sharing my screen. You can see the screen?
Yes, sir. Yes, sir.
Okay. Yeah. So the topic of today's presentation is application of particle accelerators for me, you, and everybody. And whatever the host has told about me, you already know that myself, Dr. Anurag Mishra, I am a scientific officer at Variable Energy Cyclotron Center, Kolkata. So it is a premier lab under Department of Atomic Energy, Government of India. So to start with, what is an accelerator? Accelerator is a machine which accelerates ions. It can be electrons also, and ion can be positive as well as negative. But at VCC, for the time being, we accelerate ions only, but in future we have plan to accelerate electrons also. So let us see that what type of accelerators are available. So initially, if we see the simple classification, the accelerators are of two types. First one is a linear accelerator, in which the particle moves in a linear trajectory or in a straight line. And another type is a circular accelerator. An example of circular accelerator is a cyclotron and synchrotron, and at VCC we have cyclotrons. So basically, we work in the field of circular accelerators. Then again, for the type of beam which we obtain, based on that we can again classify the accelerators as a colliding beam accelerator or a fixed target type of accelerator. So if you see on the picture in the slide, you can see that picture of Tevatron machine is here, in which protons and antiprotons are getting collided and they are taking energy from RF cavity. So in this, even everybody knows about Large Hadron Collider. So that is also a circular colliding beam type of accelerator. Another type of accelerator is a fixed target in which the beam doesn't collide but it falls on a target. So both types of accelerators are used for material science, industry, and nuclear physics application. And we all of us are having some type of accelerator in our houses. For example, a CRT TV is also an example of an accelerator. So in the picture you can see that some electrons are there which are emitted, and by the scanning electronics, the electron falls on a phosphor screen, and we are able to see the image of a picture or a moving video. So that is also the simplest form of an accelerator which we are using. So now again, if we come to the other type of classification, so at the center the accelerators and beam, and then it has various technologies which are applied in the building of an accelerator, and a lot of physics is also involved, material science is involved. So we have particle acceleration source technology being dynamics, or in the outer ring if you go in the type of accelerators, we have light sources, neutron sources, medical accelerators, ion implanters are very much popular in the semiconductor industry. Then we have industrial accelerator and collider. And then again in the outer part of the chart, if you see, you will see that the application of accelerator in education, medicine, biological science, advanced materials, finding new elements, doing research on fundamental building blocks of nature, industry, national security, and the energy generation. Now again, if we have a deeper look in the accelerators and their uses, so today almost we have 30,000 accelerators that are operational worldwide. Then again, we can classify accelerators into industrial applications as well as medical applications. So you see that industrial applications are more as compared to medical applications. And again, on the right hand side, the classification of accelerators based on their type is given. Cyclotrons, FFAG stands for fixed frequency alternating gradient, and we have synchrotrons and synchrotron light sources. Of course, written here in the star mark that this list does not include CITTV because then it will be very huge number. So now let us come to the more basic question: why accelerators and what are the applications? So whenever in the research field, whenever you want to probe a material or do some nucleophysics experiments or do some electronic interactions which happen in space or which are responsible for the generation of life on the planet and how was the life earlier, how it evolved. To answer these questions, accelerators are very important tool. Then again, if you go to higher energies, your wavelength associated with the particle reduces. So that's why you can go deeper and deeper into the nucleus. So based on that, the classification is done. So you can see in the slide that for material science research, we are at almost 10 to the power minus 10 meters or angstrom length. Then if you go to nuclear dimensions, we go down to 10 to the power minus 15 meters as well as even deeper 10 to the power minus 18 meters. And interesting particle physics are there at the range of 10 to the power minus 18. So that means you should have a very high energy accelerator to obtain that particular particle wavelength. Then again, people who are not interested in the research applications, they see accelerators as applied in medical application or industrial application. So here you can see it has a wide range of applications ranging from scientific, industrial and medical. Now, some people have a misunderstanding that accelerator is only for the physics people. It is not like that. A lot of technology is involved in building and making the accelerator and running it. So here, this slide gives you a picture that what all physics, physics specializations are required in the building of an accelerator, and even a big list there is of engineering specializations which are required to make an accelerator, design an accelerator, and finally implement it. So now again, this gives you even a more broader classification of application of accelerator that where we are using it. So this already we discussed in some of the previous slides, but again it gives a more broader classification. Like for example, linear accelerator is one type, then a linear collider, proton accelerators, free electron lasers, and for cyclotrons, we have high power proton accelerators, collision sources. So this slide covers the scientific applications of the accelerators and what all physics one can do with that. Now again, in the field of scientific application, this we already discussed, and the wavelength which I was talking about, one can calculate by lambda is given by h by p, and these are the various particles which are used, like fermions, mesons, and the bosons, which one has to discover in the material science research. One has to generate neutrons and photons, and both have their own applications. And so, in a nutshell, to do a good amount of science, you need a good amount of accelerators of varying energy so that one can address different physics problems. Again, which we discussed in the earlier slide, like particle production when the beam falls on a fixed target. So you have different types of accelerators. So this slide shows you that when beam and target is there and colliding beam electrons, Newman target generates electrons, proton as spallation targets, and products it produces pairs, mesons, and electrons, which are sub-elementary particles. And then in colliding beams, you have mesons and Higgs boson. And in the case of synchrotron radiation, it is not falling on a target, but electron is radiating. So the product which you get is the photons. So performance-wise, there are some parameters are there which are very much important for accelerators. So in the beam on target, you should take care about the flux. In colliding beam, one has to see what is the luminosity of the beam, which is generally very much popular in large hadron collider machine itself. And in synchrotron radiations, one has to see the brightness of the beam. Now let us come down to the industrial application of accelerator, in which people who are not working in accelerators are more interested. So what all applications are there that we will see. So first is the processing of polymers like cross-linking, curing, gemstone coloring to make them stronger, heat resistance, heat shrinkable, dry faster, or change the color. Then sterilization, use of electrons or X-rays to kill pathogen and prevent undesirable changes. Next one is non-destructive testing, inspection of components for flawed or hidden features. Like high energy X-rays are needed for thick components. Then most of the major share is given to the ion implantation in chip fabrication, which is very much used in the electronic industry to build semiconductors to alter near surface properties by placing ions at specific location and depths. Then finally we have wastewater and flue gas treatment to remove contaminants or byproducts of other processes. Here you can see that what is the market of industrial accelerators. So the biggest chart is of ion implantation. So it is covering the most of the part in the industry. Then you have electron beam processing, electron beam radiation, non-destructive applications. And then the US production for industrial as well medical application. Medical application we'll see in the slides to come. And finally, material processing using synchrotron radiation. So here in this slide, you can see that a lot of application of accelerators is there, and the heat market is there, and there is a lot of business opportunities in that. Because in industry, almost everything which one has to make comes from the use of accelerators. Here you can see that a picture of the industrial accelerator is given, like how our industrial accelerator looks like. So from the top you can see that electron beam comes, then in the middle that item labeled as 2 is a scanning magnet which is scan the beam on the job, and then 3 is the scanner, and 4 is the correction electromagnet. In case you want to correct the path on the job, then you can correct it with the electromagnet, and 5 is the output for that beams comes out and get downstream to the collector, and your job is irradiated or processed with the electron beam. Another very important application is the cross-linking of polymers using the electron beams. That is a typical application, industrial application of accelerators. So cross-linking is the process of bonding polymer strings together, and they can be covalent or ionic bonds. Polymer chain can refer to synthetic polymers or natural polymers. And the effect of this is to make the polymer stronger and heat resistant. This is often used to make cable insulation that doesn't melt. So you might have seen the advertisement that these Havells cables don't catch fire. So those are nothing but the cross-linked polymers. And even you can make the polymers the other way. It can also be used to make the polymer shrink when heat is applied. People working in electronics must have used the heat shrinkable tubes. So those are also cross-linked tubes. The those and the that aluminum foil, that all those things are cross-linked tubes. Now again, the description is written of the heat shrinkable film, commonly known as shrink wrap, in made of polyethylene plastic. The plastic molecules called polymers are long chain of carbon atoms strung together. Each carbon atom also connects with two hydrogen atoms. So basically, two different types of atoms are chains that will cross-link with the processing it with the electron beam obtained from an industrial accelerators. So now when the atoms are fully crossing, the plastic becomes elastic, and if you heat it to boiling temperature, it won't melt. So basically, it has become heat resistant. So after electron beam treatment, the plastic is stronger and more heat resistant, can be heated and stretched into a thin film without ripping. And when cooled to room temperature, the plastic intensives the expanded space. So place something inside such as butterball turkey and apply it, then the plastic shrinks back to its original size, resulting in an airtight packing. All these things we are using in our day-to-day life, but we don't know that all those are treated with a particle accelerator. Another type of cross-linking, what we call it as vulcanization, so which are used in our vehicle tires. So those are also treated with the industrial accelerator. So the rubber is extruded and cross-linked, bringing it into a gel state. The gel state, the plastic polymer gain more elasticity as the chain and the stress. This makes the rubber tougher and helps with further molding. The vulcanization is nothing but the cross-linking of sulfur atoms with carbon and hydrogen. And again, gemstone coloring is also an example of the particle accelerator. So some of the stones are not obtained in very good natural colors with the deep contrast. So those things are treated with particle accelerator, especially the black diamond. So those are given that particular color with the use of industrial accelerator, and it has a very good value after treating with an accelerator. Like topaz is also is actually brown, but electron beams give them a typical blue color. The same process also used in quartz, diamond, amethyst, and ruby light. So the next application of water treatment, like you have to clean the water with all the pollutants. So you have to treat the water. Here in the picture you can see the jet is treated with the electron beam. So it is down converted or reduced into a pollution-free water, and all the pollutants are converted into other products. So you can use those products if they are useful, and the water is a pollution-free water. So similar type of applications, flue gas, which is mostly obtained from the different type of industrial plants. So again, the same process is applied, that flue gas is treated with the electron beam, and it is the various particulates inside that are reduced to some other gases which can be useful, for example, methane, carbon, hydrogen, and the gas is pollution free, and then it can be released or it can be recycled for some other use. Again, this is the example of sterilization, which is very much used in the medical industry, and the antiseptic packaging. So live insect elimination, grains and tobacco, disinfecting spices and herbs without fumigation, eliminating fruit flies in fruit and vegetable, fungus treatment in food, salmonella, listeria, E. coli elimination in food. This is also very big application accelerated in the medical industry. Here you can see that how all those applications we have seen, but really the sterilization facility, how it looks like. It is not a small thing, it is a very huge facility, and there is a lot of investment involved in it. So on the left side table you can see radiation technology applied in environmental protection. We have gas, liquid and solid, and all those applications which we discussed. So what is the processes to remove these harmful products inside that, and how they are removed, and what is the physical process in transforming them to useful gases. All those things are listed out here. Now let us come to the requirement of accelerators and what energy may require, because in case somebody really wants to work on that, so they must know that what is the energy range which is used to achieve that particular product or target. So in the low energy lane, 70 kV to 300 kV. So the application of curing the pins, cross-linking, polymer sulfur sterilization. If you go to high energies in the range of 300 kV to 5 MeV, even you can go to cross-linking of wires and cable insulations, cross-linking heat and cable plastic tubing, then cross-linking plastic rubber and medical sterilization. And if one goes to 5 to 10 MeV range, bulk sterilization of medical devices and slightly thicker plastics. So, if you go on increasing the energy, then of course the cost also increases. So one has to optimize that what is the application and which range of accelerator is required for that. Now again, this is the very popular and it has the biggest occupancy in the electronics industry, the ion implantation. So on the right hand side, you can see that there is ion generator, ion extraction, mass selection, then through the beam scanning magnets, one puts that ion into a wafer. So on a silicon wafer, that ion is implanted, and then you have a semiconductor chip ready. So here you can see that what is the energy range which I use. So one can see that 1 kV to 200 kV for high current ion implanters, the low energy one. In case you want to go for medium current ion implanters, then you have 2 kV to 100 kV. And then finally your high energy ion implanters up to 5 MeV. So 1 kV to 5 MeV is the energy range for ion implantation. So about 10,000 accelerators are in use worldwide to do the silicon germanium base to create electronic industry for computer chip, and this is going to increase at a very rapid pace. Then again you have a cargo scanning, like somebody is bringing some explosive for materials which are a threat for the national security. Then in that case one has to scan the consignment which is coming, and if the consignment is very big, then on a particular truck this accelerator is installed and an image is created without opening anything, and it has a very higher contrast as compared to X-rays, and we people use the cobalt 60 sources for that, for this, for scanning it. Instead of directly generating X-rays, with the help of accelerators, the X-rays, high energy X-rays are generated to scan. Now, again, this the various types of applications, and one can see that most of the share is occupied by the industrial accelerators, and medical radioisotope and research has a very smaller share. But nowadays, the radiotherapy, which comes under the medical application, is picking up fast because it has to do with the cancer treatment, and it is very important to apply the knowledge of accelerator to save the lives of the citizens. Now, if you see some scenario of the cancer incidents, so every year millions of new cases globally, and 9.6 million deaths from cancer in 2018, and nearly 1 in 6 deaths is due to the cancer. So that's why some sort of early detection of cancer is required as well as its treatment. So treatment options we have a primary tumor, then one goes for a radiotherapy, X-ray, IMRT, and a hadron therapy later on we will discuss. But generally people go for a chemotherapy or the surgery. So here you can see that in which zone of the world which type of cancers are there, and you can see that there is a lot of there are different types of cancers. So one has to develop a diagnosis technique which can early detect the cancer as well as followed by its treatment. So it is prevalent not in one part of the country, but almost it is prevalent globally. So here you can see that hadron therapy is a particle accelerator based kind of therapy for cancer treatment. So it is not a new thing. It was proposed way back in 1946, and from there regularly it has been improving, and a lot of machines in different parts of the world has been installed, and they are regularly utilizing it. So why it is important and which type of particle one should use for the cancer treatment, this graph gives you the answer. If you have a neutrons, then it has a wider, it has a very wider. Here you can see it deposits the energy throughout the body, as well as electrons drops very fast and does not go to a higher depths, whereas X-rays also deposit throughout the body. But here if you see that 200 protons or 4800 carbon ions deposits selectively at a particular depth which is tunable. So that's why this one is very useful because it can only kill the cancerous tissue cells and does not damage the other healthy tissues. So that's why one has to go for a proton therapy or a carbon therapy kind of machine for cancer treatment. Now here this gives you a picture of proton and electron versus hadron. Hadron is nothing but protons or heavy ions like carbons. So here we have a scan which is a PET scan which is created. So you can this photograph you can see first one photons. So the dose is distributed throughout the cell, whereas in this five field photons also it is distributed throughout the cell, whereas in three field protons it is very selective, which we discussed in that graph also. So that's why it is very much advantageous to utilize the protons or hadrons, carbon ions for the treatment of the cancer. Again, PET scan is generally used to take a PET scan and see that what all at which places generally the cancer is there. So what people generally do that they prepare a compound called FDG. So how the fluorinating, because fluorinating is a radioisotope. So first you have to prepare fluorinating. So what is the process for preparing fluorinating? That you have to irradiate oxygen 18 with a proton, then you will get a neutron and a fluorinating. And fluorinating is then attached to the glucose molecule to make it a radioactive tracer. Then it is given to the patient, and then you have a gamma camera. So what happens? The cancerous tissues will consume glucose, and once they consume glucose, they will also consume fluorinating. So in the opposite direction, you will get a gamma radiation, and that gamma camera catches the radiation through the detectors, and a PET scan is obtained. So wherever dots are there, there you can see that really the cancer tissues are there. In those particular location, the this irradiation is done to kill those tissues. So in this slide, you see that there are accelerators for medicine. Like if you use the primary beam, then you have proton therapy, ion therapy, hadron therapy. If you use the secondary beam, which is obtained from the target, like radioisotopes, you have a radiation therapy or a PET, positron emission tomography. So based on that, the classification of accelerators are there. But if you produce radioisotope, then you have to transport them. So they should have sufficient half-life so that you are able to transport them to the user. Then again, if you see what are the requirement accelerator technology for the hadron therapy. So presently we have earmarked protons and carbons for that therapy. So you should have an range of 70 to 230 mV for protons and almost 430 mV for carbon ions. And this is a typical machine layout which a commercial company from IBA sells it. And then again, there are three candidates for medical accelerator. One is the electron which is linear accelerator, and worldwide it is 40,000 in number because it is cheaper technology. Whereas cyclotrons are there which gives you proton therapy, so they are 16 numbers because relatively expensive, but they are very effective. And then you have synchrocyclotrons, the synchrotrons, so which gives protons and carbons. They are more versatile machine, but again very expensive. So that's why they are very low in number. And here you can see that nowadays people are coming up with a tabletop kind of machines so that you can see a person is climbing on top of that. This is the only size of that. And then you have a large gantry is there, big line is there. So it is a full-fledged setup and a big setup. So this is what we have at Kolkata. This is the medical cyclotron which we have set up at Kolkata Center. And here you can see that machine there, it is not very big. And then it is continuously delivering a lot of radioisotopes to the requirement of cancer patients in the eastern part of the world. And recently it was also in the news that cancer diagnosis for setup to deeper cyclotron gets functional. And this is a different type of radioisotope which it is producing with their reactions, beam energies and beam current. Now there are some open questions for future also, like because this is what we have done, but now new young people and the students must pick up that how to go to 350 MeV and cyclotrons, ligate boosters, cyclotrons, and carbon machines are there in abroad, but in India it is not there. So the younger generation has to take up this challenge because for the betterment of society, that how to improve the cost and whether carbon or even heavier ions will be useful for that or not. And you can see that black peak of the carbon versus proton. So definitely carbon is more advantageous because you have to go to higher energies. So that is some technological challenges which I think people will address in the near future. That is a very interesting application of accelerators. Like nowadays, a lot of fake products are there in the market. So one person in abroad has used accelerators to know that whether the wine he has got is real or not. This is also very interesting application of accelerator. This is the conclusion slide. A very famous statement by a very famous physicist. So education is what remains after one has forgotten everything he learned in school. So from there onwards, the research starts. And there is no applied science if there is no science to apply. So one has to learn and apply. Then only technology is going to improve. The task of the mind is to produce future, and this is what you can see that 0.2 nanometer DNA nucleosome has been reconstructed with the help of an industrial accelerator. So thank you for your attention.
In simple manner. In this lecture, he has explained the applications just for purification of water, for cancer treatment, FDG sugar, accelerators for medicine, wine, thought, etc., etc. I very much thankful Dr. Anurag Mishra for his informative and excellent talk. Thank you, sir. Thank you.
Thank you, Dr. Revatkar sir, for nicely conducting this technical session 1. I'm also thankful to Dr. Professor Sanjay Doble sir and Professor Anurag Mishra sir for nicely presenting their expertise and enlighten us. Now, after this, there will be technical session 3, in which we will have resource person, Professor Abhay Kumar Singh sir and Professor Gordon sir. And this session will be chaired by Professor R.G. Atram sir. R.G. Atram sir is currently working as a director of Institute of Science, Nagpur, and he will conduct the session. So I request Dr. R.J. Atram sir to conduct the session. Over to Atram sir.
Thank you. Dear participant, in this session we have with us Professor Abhay Kumar Singh. He is from Atmospheric Research Laboratory, Department of Physics, Banaras Hindu University, Varanasi. In his credit, more than 416 publications in national and international repute journal. He himself designed and started new specialization in his university, space physics. He is a fellow member of many professional bodies. He is an editor and reviewer of many research journals. we have such a prestigious and nice personality with us. He will speak on space weather, cause and consequences. I request Professor Abhay Kumar Singh, please deliver the special talk on space weather.
Thank you, sir, for giving a nice introduction. I am very much thankful to the organizer for inviting me and giving this opportunity to present my work. Here with not a, we are delayed. He's worried about the lunch. Going directly to my lecture. So I am sharing my slides. I hope slide will be visible to all. So
Yes,
my
sir.
topic is space with its consequences, its causes and consequences. This is a very, very hot topic nowadays. And it is very, very good for the young minds who are working space physics, atmospheric physics. So this presentation I have designed for mostly for young faculty. And what are the space weather, what are their causes are responsible, and how this is affecting our near earth environment is very important. So the plan of my talk is divided into several parts, and first I will give the brief introduction about the space weather. What is space weather, why it is so important, and then we talk about the some space weather events. I have given some videos from the different satellites about the space weather to give the audience influence about the space weather, and then we talk about what are the different effects of a space weather, how they are affecting our near earth environment, our day-to-day life, our communications, our satellites. And then I will go to the different facility available in our laboratory of atmospheric research laboratory at Banaras Hindu University, Varanasi. And then I will give you the brief idea about the global positioning system measurements, because we are making here GPS measurement. It is a instrument to study the space weather phenomena. And then I will present some results. What are the effect of a space weather on the ionosphere due to the solar flare, due to the geomagnetic storm, and due to the solar eclipse event? How these events are affecting our ionosphere. So space weather is nothing but it is a variation in the solar energy, their emission, prominences, and the different CMEs. So it is a variation in the solar wind, the magnetosphere, ionosphere, thermosphere, which can influence the performance and reliability of variety of a spaceborne and ground-based technology. Basically, the space weather is the weather between sun and earth. What is going on directly on sun and how it is affecting our near earth environment on the earth. So this is called space weather. It is very much important because they are affecting our satellites. So a space weather is recognized as the cause of significant errors experienced by global satellite navigation system, that is the GNSS receiver. It also affects satellite-based augmentation system and their uses. That's why there is a need to study space weather in details. What are their causes? What are their consequences? And that's why I have chosen this topic for the audience. So the sun is the important parameter for a space weather. So we have to know about the space. The sun has an interior and atmosphere. The interior of the sun is divided into three layers. The innermost region is known as the core, where thermonuclear reaction is going on, and two hydrogen form the helium, and lots of energy in the form of gamma ray generated. Second is the second layer is the radiative zone, where radiation is dominant, and this radiation propagates in this region, and they converted to gamma ray to ultraviolet and the visible. And third layer is the convection zone, where convection cycles are dominant. These convection cycles are basically the plasma coming from interior of the sun to the surface due to temperature gradient, and this plasma moves from sun to earth, and they come on the surface. Sometime they produce sunspots and the prominences, and plasma will go from one sunspot to another place. They are known as solar prominences, they are known as solar jets, they are known as solar flares. So these are the solar active regions seen on the solar surface. So a space weather starts from interior of the sun to the surface of the earth, and these space weather events are very much important to study the space weather phenomena and its consequences. So the solar active regions are sunspots. These are the sunspots which is seen, and the Galileo was the first who have photographed the sunspots. They are the basically cooler and darker regions seen on the surface of the sun. They look cool because their temperature is less than the surrounding, and their sizes are very large. They vary from 10,000 kilometer to 30,000 kilometer, and it is bigger than the size of the earth. So they are mostly occurs in pairs and groups. One has a positive polarity, one has a negative polarity, because they are magnetic regions. They have a high magnetic field, and these solar active regions produces the solar flares, prominences. Solar flares are the sudden burst of energy in terms of radiation as well as the particle which is emitted in 4 to 5 minutes the whole universe, and the energy is so much. It is order of 10 to the power 26 joule energy is emitted. And there, due to these events, solar active regions, there are coronal mass injection. The mass of the plasma will move in solar system and the outer system of the corona, and they affect our near Earth environment. All the solar system will be affected by the coronal mass injections. So solar magnetic loops are seen. So when there is a group of sunspots, if you see the group of sunspot, plasma for one reason or another will move, and this will also known as magnetic loops because there is a magnetic field. So they cross each other, and sometimes they grow and grow and grow, and they becomes larger at thousands kilometer, and they curl and twist, and then they sometimes they erupt, which is known as erupting prominences. So you can see erupting prominences. You can see the very much size, longer size. You will see the erupting prominences. Beautiful erupting prominences can be seen, and they erupt, and sometimes part of this energy will go to the whole solar system, and they affect the near Earth environment, and they release lots of energy known as solar flare. So what are solar flares? Sudden and explosive release of energy, 10 to the power 90 to 10 to the power 25 joule, which is in localized region of the sun, and they generates the solar wind and radiation also. So different kinds of radiation emanate, that is the X-ray, gamma ray from the solar, and they occur in the active regions around the sunspots. So they influence the whole solar corona, and their sizes are very large. So these are very, very effective phenomena for the solar physicist and the space weather. How the sun and earth is interacted, what happens when the solar activity will affect. So you have seen these solar active regions. This is the sun, the active sun, different layers we have already talked about, and these are the solar active regions. These are the places, these are the corona, these are coronal mass injections, sunspots. This is the sunspot and the photosphere. So this plasma will move, and when it moves toward the earth, earth has its own magnetic field. So earth has a magnetic field, earth has a north pole and south pole. So plasma coming from north to south, and they will move in this way. This is dipole magnetic field. But when solar particle will come, they compress the base side. So the plasma coming from the sun, the ions and electrons, high energy ions and electrons coming from the sun, this incoming solar particles, we call it solar wind particles, compress the day side magnetosphere. So earth day side magnetosphere is compressed, and night side is elongated and stretched. So we have a cavity which is known as magnetosphere. So this is the cavity which deflects the plasma, and plasma enter from the tail regions, and they reach around the earth. So there is a connection between the sun and earth. Directly or indirectly, the sun affects our near earth environment, and we have a large changes in the surface as well as the ionosphere, magnetosphere, as well as the earth atmosphere. So there is a direct relation between sun earth connection. So this can be seen by this video. I will show a video. This is the active sun, and the active sun is going on, and when sun is active, the plasma and radiation emitted from the sun, so this radiation is going on, and they are moving in the whole solar system. They passes through the different planetary system of the earth. They compresses the day side and elongated in the night side. So this is the reason when the solar particles will go and they produce the aurora. So these particles enter in the system and they produce the aurora. So this is the most important effect. Aurora is seen in the 70 to 80 degree northern latitude and southern latitude, which the sky becomes blue, the sky becomes red, and this sky becomes violet in the different auroral region. 70 to 80 degree north and 70 to 80 degree south. That is the Sweden, Norway, Finland, as well as the Canada. And the south it is New Zealand and Australia, where the aurora is seen. I will show you some aurora also. So these are the direct evidence. So how the filaments will are. So you will see the video. This is the video taken by satellites, the close view of prominences. You will see the prominences are growing and growing and growing and growing. So group of sunspots will generate and their sizes of this filament grows. So they go to several thousand kilometers in the sky and they are the active regions. They in terms of radiation, in terms of plasma. So how the formation of solar flare is seen. So solar flare, you will see here, the prominences rises and they erupt, we known as erupting prominences. So there is a curling and twisting of the magnetic field and the plasma. So this twisted and curled magnetic field lines, sometimes they grow and they release energy. So energy is too much large, 6 joule, and they affect the coronal mass injection. So this is the video of the coronal mass injection. You can see very closely the plasma is emitted on the whole system. A large of the particles are ejected. And this video you can see the comet. 2 comets are also falling inside this. This is interesting video which shows that 2 comets are also falling in the sun. So this is the coronal mass injection and the formation of aurora. How aurora will be formed can be seen by this video. This video you see that prominences is formed and a plasma loop is formed and this energy is released. So when this energy is released in the outer atmosphere, they come in the solar system and they come to the whole solar system. They come to the Jupiter, Saturn, Uranus, Mercury and Earth also. So they affect the different magnetic field of the planetary system, and that's why a magnetosphere is produced. They affect the satellite system also. So this is the magnetosphere. A cavity is formed. A cavity is formed. This is the 3-dimensional object, and this is the day side, and this is the night side. So here is the Earth, and particles are interacting here. They go from the night, enter inside the magnetosphere. They come to the 70 to 80 degree northern and southern hemisphere and they produce the green aurora. So this is the region where aurora is seen, and this is the beautiful aurora video. You can see how the sky becomes red. This particle entered in the Earth atmosphere. When they entered in the Earth atmosphere, they interact with the neutral particles or ionized particles. They give their energy and there is a auroral display. So this is known as aurora borealis and aurora australis in northern and southern hemisphere respectively. So this auroral display, you can see the sky becomes blue, the sky becomes green, the sky becomes red, and they have a curling and folding like a curtain blend. So this is the beautiful photograph of the aurora borealis. You can see the different aurora and how the effect of a space weather on communication. So these space weather particles, the space weather event, the solar flares are affecting our communication. We are using the mobile technology, we are using the TV technology, we are using the different communication system by our satellite communication. So since these are produced and affecting our whole system, our satellite is affected, due to which the communication will be affected. So a person is watching a TV and he is watching a dance program, and you will see at once satellite is transmitting, this is the inside city satellite, it is transmitting the signal to the ground, and person is watching the TV, and as soon as the solar wind particle will come, they produce ED current and they produce the phase lock loop, and due to which the transmission is degraded for few, and there is a phase lock loop. The signal phase is locked and we have a no control on the signal, and few minutes our transmission is degraded. This is due to the space weather effect on communication. So space weather produces a large effect on communication. So there is a need to study the space weather. We have to quantify the effect of space weather, and then we can enhance our telecast and telecommunication by this. How they are affecting our satellites. So this is a satellite which is moving in the space, and this solar wind particles has come, and this particle has produced a change in their path, the change in the solar panel, the change in the body of this satellite, and the satellite is damaged. And sometimes satellites turn their path and they will be taken out of the orbit and comes in the Earth atmosphere and they are born. So the life of the satellite is also affected by the space weather. So these space weather particles are affecting the life of the satellites, the solar panels, the body of the satellite, the sensor of the satellites, and the satellite's path is changed. Satellites damaged due to the space weather phenomena. So these space weather are affecting our different satellites, and we are living in the world of satellites. Without satellite, nothing is possible nowadays. Modern era is affected by the satellite. So space weather is responsible for the satellites. So these sunspot and the active regions have a cyclic variation, and it is observed from 1600 to 2020 that there is a variation in the number of sunspot. The sunspot number is the measure of the solar activity, and we found that there is maxima and there is a minima. You can see there is a maxima and there is a minima, and they have a repetition of 11 years. So this cyclic variation has a repetition of 11 years. After each 11 years, there is solar maximum period and solar minimum period. So this solar maximum and minimum period is known as solar cycle, and solar is active. So this phenomena is known as solar cycle variation. After each 11 year, this maxima and minima will comes. This is the periodicity of sunspot, and this solar activity also shows a periodicity of. So how the Earth magnetic field is powered? This is the Earth magnetic field. Already I have shown you the magnetosphere. This is the Earth is here, the magnetic field here. So day side is compressed, night side is electron. It is 10 Earth radius and it is 60 to 80 Earth radius. And this cavity is known as the magnetosphere. We are living in safe in this cavity, and there are several active regions which is studied in the Earth magnetosphere. So these all are affected by the another important layer is the ionosphere. Ionosphere is the layer where ions and electrons are found. This layer varies from 60 kilometer to thousands kilometer. You can see altitude for 60 kilometer, 1000 kilometers. The electron plasma density has a large, and this is a layered structure which known as D layer, E layer, F1 layer, and F2 layer. In the day side, the layers are D layer, E layer, F layer. F is also divided into F1, F2. The height varies from 50 to 90, 90 to 150. And F1, F2 will have maximum electron density. So ions and electrons are seen. In the day side, the ions and electrons are seen. And these ion electrons will affect, because they are dispersive medium, they affect our satellite communication. When there is a solar phenomena, the ions and electron will produce more and the communication will be affected. There is a formation of plasma bubble. There is irregularity in this medium, and it also affect the different satellite communication systems. So ionosphere is very important. So this cartoon summarizes the different effects of space weather. The space weather effects starts from the astronauts. The astronauts moving in these satellites like Kalpana Chawla and Sunita Williams, they have to wear space dresses because these particles will make a DNA rapture. So this particle will produce a rupture of the DNA, so they have to life in danger. There may be cancer, there may be different types of diseases. So they have to wear dresses, special dresses, but in spite of this dress, they have a danger. So these solar wind particles affect the astronauts' safety. And these particles satellite the satellite. I have shown you a video also how satellite is degraded. They burn the solar panels. Sometimes they produce the ionospheric current. In the ionosphere, they produce the plasma bubble, due to which the communication is degraded. They affect the formation of water formation and cloud formation also. It is indirectly affecting the cloud system. They also produce the GPS navigation system. They also affect the communication system, radio burst. They also propagate the problem in the pipeline corrosion and the telecommunication cable. Some the internet is also affected by the space weather. So you will see the from upper atmosphere to the lower atmosphere and the inside the earth also the space weather is affecting. So that's why the space weather is a very important topic of the day, and lots of research and awareness is needed. And the remedies can be done to minimize the effect of space weather on the different system of our day-to-day life and the earth and atmospheric physics. This is the beautiful diagram of aurora. This is the beautiful diagram of aurora. You can see how it looks. X-ray rates. These are taken from Sweden. And another effect of the space weather is the geomagnetic storm. So when a space weather phenomena occurs, the earth magnetic field is affected. Due to the effect of this space weather, the earth magnetic field changes, and you will see that DST index is the measure of the geomagnetic storm. DST index is the storm time index in nanotesla. It is measuring the horizontal component of the earth magnetic. And you will see that earth magnetic field is 0. At once there is a sudden commencement of a storm, and the magnetic field start to decrease and decrease and decrease. They comes to a minimum. Here it is minus 200 greater than, and then it starts recovering at come to the 0. So this region is known as geomagnetic storm. So when this Earth magnetic field is disturbed due to the space weather phenomena, different types of changes is found in the near Earth environment, and these is classified into weak, moderate, and intense storm depending upon the DST index. So are very much important, and of the geometric storm on ionosphere is a subject of a hot research nowadays. And here I will summarize the different instrument available in Banaras Hindu University in the atmospheric research laboratory. We have a very high frequency receiver by using the Yagi antenna and the chart recorder. We have a very low frequency receiver. So this very low frequency receiver is very much important to study the D layer of the ionosphere, the lower layer of the ionosphere, and the GPS receiver. We have two GPS receiver, Trimble and the GNSS receiver, multi-frequency GNSS we are using here. So we are measuring the ionospheric effect, the effect of a space weather effect on ionosphere, the ionospheric total electron content in measurement measured in day-to-day basis, and we have a L-band receiver also. Apart from this ionospheric phenomena, we have an automatic weather station to measure the surface temperature, pressure, humidity. We have an automatic visitor detector. We have a LIDAR. This LIDAR is used for measure the atmospheric aerosol, and we have a pair of microtops to measure the column AOD, aerosol optical depth, to measure day-to-day variability of the dust particle, the aerosol particle, the particulate matter, and these instruments are very much important to study the atmospheric phenomena. We have two high volume samplers we are using to measure the particulate matter of 2.5 micron and 1.0 micron, as well as PM10 micron. So these all three size particles of the aerosol will be measured basis, and we are measuring in environmental studies. We have a net radiometer to measure the net radiation from sun. They are measuring the difference of the upcoming and downgoing radiations. This is a very important phenomena, and one of the carbon is measured by the anthelometer. So anthelometer is the instrument which measures the black carbon. So black carbon with the absorbing aerosol, which is responsible for the global warming. So we are measuring these instruments in Banaras University. I am not going to present the all results. I am going to present the space weather phenomena and their effects. So I will present some of the results using the effect of a space weather. We have also installed a solar measurement telescope. So this telescope is a solar telescope. We have equatorial reflector telescope, and it has a solar filter. 99% we block the ultraviolet radiation. It is equipped with a CCD camera. The CCD camera, we can photograph the different views of the sun and the moon or any planet you can measure. And also you can measure the stars, but here we are using for solar measurement, and they have a spectrometer to measure the different range of the spectrum of the sun. We can measure different experiments: solar limb darkening effect, sunspots, their solar flare, the sun rotation period, the solar rotation period, the solar eclipses. So recently in June we have a solar eclipse, and lots of photograph of the solar eclipse have been measured. So he different the sunspots, the moon, and so this is good for the students as well as the research purposes. We have a special space physics program here. We are running in Banaras University. The specialization is space physics, and students are getting degree, and they are going directly to the different laboratories of ISRO's, Indian Space Research Organization. So our students are trained, and they got different research and technological position. So brief introduction about the GPS. We have two GPS. GPS is a global position system which measures the position of the point of the globe. It has a three segment. One is known as a space segment, control segment, and user segment. The space segment consists of a different 24 satellites in 6 orbit, and control segment measures the different control parameters at different stations, and user segments any person who has a GPS receiver can measure. So this is used for measurement of the parameters. You can see the 24 satellites are moving at different orbits. There are 6 orbits, so there are four satellites in each orbit is moving. They are moving at the height of 20,200 kilometers. They have a speed of 4 kilometers per second, and they have a period of 11 hours 58 minutes. They are sending two signals of L1 and L2, 1.5 gigahertz and 1.2 gigahertz. This is used for a study of the total electron content of the ionosphere, which is a very, very important. These are the control stations made in the different places of the globes. They are designed that any place you will find some locations, and we can measure the exact value of the location of that point. So this is very important devices. And here I am presenting few results. I'm not presenting all because this is the research purposes. So I am just giving you effect of solar flares on ionospheric total electron content. How solar flares are affecting our ionosphere. So the solar activity is seen, solar flares are seen, coronal mass injection are seen. So this is the solar flux measured by the GEOS satellites. X-ray flux is measuring, and they found a large increase in the X-ray flux as soon as the solar flare comes. So it gives the solar flare, and we are measuring the vertical total electron content. Here you will see the electron content is a constant, but as soon as the solar flare will come, the electron content goes to increase into 16%. Sometime go to 40%. There is change in 10% to 40% due to the solar flare. So these solar flares increases the ionization and the dynamics of the near-earth environment. There are so many regions, but directly they are affecting our formation of the total electron content. So here you will see the intense solar flare. It is a X-class flare, X-class flare for X6.9 flare, and this flare is a very active flare. And when this occurs, the total electron content and flux have a large increase. You will see the solar flux has increased, and due to the solar flux, the total electron content increase. There is a total electron content, and the total electron increases. And when we measured by the satellites, we found the large change in the production of the total electron content, and this in the different regions, D region as well as the E region and F region. D region, the X-ray is responsible, and the E region you will see here the responsible different formation of the ionosphere. So geometric storm results are also presented here. This is a geometric storm. This is DST index, and you find the DST index has gone. It is occurred in 26 September 2011, and you will find that the TEC at the DST has gone to a minimum of minus 120 nanotesla, and then it recovered. It lasts for around 5 days. And the solar wind parameter has also gone in. Generally, the solar wind velocity is around 400 km per second, and it's gone to 700, and then it starts to decrease. In the same day, the solar wind density has increased, and the magnetic field, interplanetary magnetic field, is also changed, and they become southward. So when they become southward, the magnetic reconnection will start, and it has increased the total electron content. And so you will see that there is increase in total electron content, and this increase in total electron content is around 46%, and this is due to the wind lifting effect, and the electric field was too weak to produce such enhancement. So there may be storm induced phenomena, and there are several regions of this storm, and dynamics is changed by the different mechanism. There are so many mechanisms to study this, and there is a response of the solar low latitude D region ionosphere due to total solar eclipse. So this is on 22nd July. The total solar eclipse was seen, taken by the telescope. So the shadow of the moon, sun, and we are not able to get the radiation, and the total solar eclipse has occurred. The path of totality passes from Varanasi, and we have 100% totality. So this is the path and the track of the solar eclipse, and we are measuring the signals. The signals are passing through this region, due to which there is a amplitude has a large change. This is the start of the eclipse. This is the totality, and at the time of totality, the magnitude of the amplitude has gone large. And one day before and one day after, there is no such changes. So these changes has found around 100% change, 120% change. So this has shown that the solar eclipse covered the moon, and due to which the solar radiation is not coming, and it has decreased the production of the D layer of the ionosphere, and due to the D layer is degraded. So we will see that this affecting our near earth environment. Here also we have studied the RIA-TEC prediction and GPS-TEC measurement, and the GPS-TEC measured by the global position system as well as by the international reference ionosphere, and there is a change in the total electron content day-to-day basis as well as the summer, winter, and equinox. Equinox has a maximum change, and this has found a winter anomaly in the month of the winter. In November, December, there is a large change in the content which is recorded. So we have got opportunity to study the total solar cycle. I have talked about the solar cycle. Solar cycle is the variation of the solar sunspot number and the solar flux. Here, this is the recent solar cycle which has completed in 2019. So here we are presenting the 2008 to 2018 total 11-year data of the solar flux as well as the total electron content at the Varanasi, and we see that there is a maxima and there is a minima. So electron density start to increase and decrease. This is very much correlated with the solar flux as well as sunspot, and there is a direct relation with the production of the ionospheric. And also we compare it by the different models. One of the model is the RIA, International Reference Ionosphere model, and one of the GCM model. So both these model we have tried to study, and there is a good agreement between the GPS, the TIC GCM as well as the RIA model. So these all have been shown there a good relation between the solar phenomena as well as the solar cycle variation of the total electron content. So now I wanted to conclude what we have seen by this space weather. What are the space weather and what are their consequences and how they are affecting our near Earth environment. The space weather events influence the whole ionosphere over low latitude. Intense solar flares respond to the ionospheric and they disturb both D and F region of the ionosphere. D region ionosphere is perturbed by during the solar flare, and this will be caused by the flare time enhanced level of photoionization due to X-ray flux, and enhanced UV flux is affecting the E layer and F layer. The geometric storm is also affecting. This is maybe the fountain effect or the storm induced wind lifting effect. Very vertical TEC is produced by the GPS positioning. They are affecting the errors in the GPS, due to which the GPS is not able to work properly, and there are so many degradation. There is a great need to study the understanding the variability of low latitude ionosphere using the space weather events. That's why the space weather event is the hot topic. The space weather event must be needed to be studied in detail. The space weather phenomena, that is solar flare, the sunspot, the different active regions are needed to be studied in details, and this must be put on the student level. Still we are not giving this in US, in UK. This topic is a hot topic for the K2 level, the intermediate students. This topic must be introduced to intermediate students, and they have to be aware about the space weather phenomena, about the weather between sun and earth, the effect of the sun, and we have to study in detail. Thanks to you. I'm also thankful to the different ISRO and the ISRO program to BHU to providing the fund to study. I'm also thankful to the organizer giving this opportunity, and I will happy to give some answer and queries of your questions.
Any questions? Any questions from the participant? If there is no questions, thank you, Professor Singh, sir. You have given very interesting lucid talk on space weather, which is an integral part in the atmosphere. You have nicely explained sunspot, solar flares, solar corona. Now sun and earth reacted, how they are reacted, formation of aurora, earth magnetosphere, formation of green aurora, geomagnetic storm, solar flux. You have also nicely explained effect of space weather on communication system and many more. I am sure our participant must get benefited with this talk. Thank you, sir, once again.
Thank you, sir. Thank you, Atram, sir. Thank you. Thank you.
Thank you, sir, for delivering such a wonderful talk. And I would, on behalf of the Gondwana University Gadchiroli and the CONIAPS, International Conference on Advances of Physics, I thank Professor Atram for chairing this session. So thank you very much, Atram, sir.
Thank you.
Thank you, Sandeep.
Thank you.
Now we shall now the third technical session is over. Now we shall move on for the oral presentation sessions. So for that I request Dr. Changam Mungmode to chair the session. Mungmode sir, please.
Okay, thank you, sir.
Okay. So I shall introduce Mungmode sir.
No need, no need, sir. Okay.
Okay.
So, very good afternoon to one and all. Now again, we are heading towards the oral presentation. So this is the day 2, and before we start oral presentations, let me tell you some instructions. Presenters should present their work within 6 minutes. Okay, this is the major instruction. So by keeping the time constraint, you should have to make your presentation. So for oral presentations, I think very few participants are present here. First of all, I will call upon HB Mishram sir. Am I audible, sir? Mishram sir. Hemant Kumar Mishram sir. Mishram sir.
Mishram sir.
Hello, hello.
Yes, sir. Sir,
Sir, you can make your presentation now.
You are presenter now. So please share your slides.
Sir, am I audible?
Yes,
Yeah,
sir.
yeah.
Sir, you are audible, but share your slides. Share your presentation.
I'm sharing my presentation, sir. Please. Visible, all of you?
No,
Is my
no,
PPT
no, sir.
visible? No.
No, sir.
So now it is visible?
No. No, sir.
Meshram sir. Hello.
Mishram sir.
Meshram sir.
I think he had some technical difficulties. So before he get ready, we'll go to another participant. The next participant is Dr. R.G. Vidate. Vidate sir, am I audible? Dr. Vidate sir, am I audible? Vidate sir, you are now the presenter. You can make your presentation now.
Hello, sir.
Sir, you are audible. You can share your.
Am I audible, sir?
Hello. Yeah, you are audible. You can share your PPT now.
Yeah. Can I use mobile?
Yeah, you can use mobile, but you share your presentation. You share your PPT or PDF, whatever.
I have PPT. On your mail, yes, okay. 1 minute. Sir, I have sent my PPT on your mail.
Sir, on which mail you sent your PPT?
Mail PISL or any or your mail is you can you have sent the mail of link of this conference.
Actually, we have not received your mail till now.
After this presentation.
Okay, Mishram sir, are you ready? Yaman Kumar Mishram sir.
Sir, I am ready, but how to share my presentation, I don't know, sir.
See, we can make means we allow to.
I'm trying to present on or
Now you are the presenter. Now there is one tab on your screen, share. So from that share tab, you can share your PPT.
sir, there is no screen sharing tab.
One.
Shyam sir,
Yes, sir.
is it possible to please send your PPT to the conference email so that we can share it, then you present it from there.
Because that sharing PPT or sharing is not on my device.
Okay. For that, I am giving you a solution. You email that presentation to the conference email
Okay, sir.
covid26@gmail.com.
I'm mailing to you, sir.
Okay.
Sunil Chute sir. Chute sir.
Sir, Amit Kumar is present.
Yeah. We'll heading towards the next presentation. Dr. Amit Kumar is present here. Am I audible, sir?
Yes, sir, very much audible.
Okay, so sir, you are now the presenter. You can make your presentation.
Okay. So let me share On my screen now.
Sunil, Brunal Yavalkar ma'am is also there.
Okay. I hope my screen is visible.
Yes. Saud Alwadi is also there in attendee. You can take them to panelist. Sunil.
Yes.
Saud Alwadi.
Saud Ali. Okay.
Ishita Ghosh ma'am is also there.
Okay. Sir, not make panelist. Ishita Ghosh. Such problem. So I think my screen is visible. May I present or
Yeah.
wait for?
Yes, it is visible.
So good afternoon, all of you. My name is Dr. Amit Kumar. I am from Bhaskaracharya College of Applied Sciences, University of Delhi. Today I wish to present a review for the recent trends in the VLSI designs and future alternative due to nanotechnology. This is the title of my presentation. If we see the last 50 years, how the IC's feature size has reduced from micrometer, 10 micrometer to now 5 nanometer. This 50-year journey have taken us from big mainframes to small, smart handheld devices. So the advent of civilization is totally dependent upon the the advent and progress in the field of electronics, and which is only due to the VLSI designing. This is the journey that we have seen in last 50 years, and the word has seen
Amol म्हणून एक आहे.
the word has seen
Amol
the
आणि
transition
Amol आणि
from
Ishita Ghosh.
heavy machinery to the
आणखी
sophisticated
कुठे
device.
लिस्ट मधले आहेत पाहून घे थोडस.
Okay. So if we see before 2000, as we scale down MOSFETs, the good thing resulted automatically, like chip gone faster and they consumed the less power. And this gave the extra processing speed, and the power is going less. Therefore, the more and more portable devices are coming from 2000 onwards. Now, in early 2000, when the chip feature size began to shrink below 90 nanometer, this automatic benefit begins to fade. At such a low dimension, as the electron moved faster and faster in smaller and smaller silicon circuits, the chip began to get too hot. And this heat is the fundamental problem. So even though the size is shrinking, the electron has to move faster and faster in between the smaller and smaller areas. And this gives the heating effect to the material. And this causes this is referred as heat death of Moore's law. And it required immediate solution in early 2000. What were the immediate remedies? Immediate remedies was the manufacturer stopped increasing the clock rate, and they limited the fast operation of microprocessor. And the noted fact is that the maximum clock rate since then is not getting any increase further. But how to make our cells to move along the Moore's performance curve? What we done was, despite of clock speed limitation, the microprocessor chip contained not only one processor but multiple processors. and these are now referred as cores. So dual core, quad core, octa-core microprocessors are commonly used today. So we may have the situation where the same output with the 4 cores at working at 250 megahertz will give you same output of 1 gigahertz processing. Now, what are the current challenges? Basically, as the feature size has reached the classical physics limitations, so the devices needs quantum mechanical explanation, and designing at such a low scale of integration requires high-end equipment, which is not possible for the small scale establishment working in the field of VLSI designing. So basically, we are living in a transition period where the classical way of chip making is about to get replaced by emerging technologies due to the advent of nanotechnologies. What are the advantages of nanotechnology? Nanolithography. There are two ways in which the nanolithography plays an important role. First, the techniques that are capable of etching away the molecules and leaving behind the desired structure. And second, the techniques that are capable of writing the desired structure to a surface and making the 3D printing that creates the desired structure. Out of many nanolithography processes, dip pen nanolithography involves the scanning probe, the nanopatterning technique in which the atomic scale tip is used to deliver chemical and biological region, and they are termed as inks, and they directly write on the substrate as a nanoscopic region of target on the substrate. So they were basically I have written a review article of 20 pages, and in through them I have picked two main works that are going to be utilized in coming days. One of them is done was Sander J. Trans. What they have fabricated is they have reported the room temperature transistor based on single carbon nanotube. Basically, they fabricated the field effect transistor, that is a 3-terminal switching device that consists of non-semiconducting single wire carbon nanotube connected with two metallic electrodes. On the application of the voltage to a gate electrode, this nanotube can be switched from conducting state to insulating state. So this is basically the function of MOSFET, and that can be accomplished by a carbon nanotube. And this device was reported to work fine at the room temperatures. Therefore, it has shown the potential to be used in the practical applications, and working with this nanotube transistor is explained by semi-classical band bending model used for the traditional semiconductor devices. The successful working of 3-terminal switching device at a single molecular level represents the important breakthrough towards the molecular electronics. So what I am suggesting is, what I am getting is, point I have to mention here is that we are about to move from VLSI designing to the molecular electronics, where the molecules themselves plays the working of electronic functioning. Another example is single atom transistor. Basically, in this transistor, the individual phosphorus dopant atom were deterministically placed within the epitaxial silicon device architecture with the spatial accuracy of one lattice. That is, only a single lattice is used to make a transistor, and the phosphorus is placed in between as a dopant atom. The operation of this transistor was done at helium temperature with millikelvin electron transport measurement. And it was confirmed that the presence of discrete quantum energy levels in the energy spectrum of phosphorus atom. But the working is performed at the cryogenic nanoscale semiconductor device. This is basically cryogenic nanoscale semiconductor device, plays an important role for the wide range of applications like quantum computer, since these devices exhibit fast operation, low power dissipation, small leakage current, reduced noise, and thermal degradation as compared to their room temperature counterpart. However, the quest will always be to make such devices working successfully at the room temperature. So these are the two main focuses that are going to play an important role in the coming days for the replacement of VLSI technology.
Excuse me, Amit sir. You have to finish your presentation within 1 minute.
Yes, yeah, I'm just about to conclude. These are the main devices that are going to play important role in the coming days. These are under research, but they are means moving from research area to the industrial area. Now, I conclude by saying that the study shows the alternative designs with the advances in the nanotechnology are going to play only a temporary role, while ultimate destiny will be based on the biological, molecular, atomic, and spin-based electronic, and the first VLSI design will get deleted altogether from the chip manufacturing. With that, I conclude my presentation, and I thank the organizer for providing me the platform to share my views. Thank you very much.
Thank you, Dr. Amit Kumar sir, for making such a nice presentation. Now we are heading towards the another presentation. Dr. Mrunal Yawalkar ma'am is there. So I request Mrunal Yawalkar ma'am to make her presentation.
Okay. Thank you, sir. Am I audible, sir?
Yes, ma'am, you are audible.
So is the PPT visible clearly?
Yes, ma'am.
So I'll start, sir. Good afternoon, one and all. Myself, Dr. Mrunal Yawalkar. I am here to discuss about the gadolinium activated luminescent materials for phototherapy lamps to cure psoriasis. I am working at present under the guidance of Dr. S.J. Doble, professor from Department of Physics, RTM, Nagpur University. It becomes necessary for us to know what is psoriasis before we move on to the luminescent materials. Psoriasis is a non-contagious chronic autoimmune disorder that causes rapid multiplication of skin cells, leading to red, itchy, scaly patches on the skin. Psoriasis patches can range from a few spots of dandruff-like scaling to major eruptions that cover large areas. Most types of psoriasis go through cycles, flaring for a few weeks or months, then subsiding for a time or even going into remission. These are certain types of psoriasis. The first one is plaque psoriasis, in which dry, raised red itchy skin lesions covered with silvery scales can be seen on elbows, knees, lower back and scalp, as it can be seen in the figure 1. The second type, nail psoriasis, in which peating, abnormal growth and discoloration of fingernails and toenails takes place. Psoriatic nails might loosen and separate from the nail bed. It is seen in figure 2, and severe cases may cause the nail to crumble. The third type is gutted psoriasis, in which is triggered by a bacterial infection and occurs usually in young adults and children, where small drop-shaped pink red lesions appear on the trunk, arms or legs. The fourth one is the inverse psoriasis, which is triggered by fungal infections and smooth patches of red skin that worsen with friction and sweating in the skin folds of the groin buttocks are seen. Pustular psoriasis is a rare form of psoriasis where pus-filled lesions occur on the palms or soles of the feet. Erythrodermic psoriasis is the least common type of psoriasis. It covers entire body with a red peeling rash that can itch or burn intensely. The last, the psoriatic arthritis, it causes the joints to swell and they are painful, and it is typical of arthritis. So the treatment of psoriasis started long back by phototherapy. Phototherapy is a brief exposure to non-ionizing ultraviolet radiations, and it has been used widely since ancient times for the treatment of psoriasis. Sunlight is the most common type of phototherapy, but sunlight has a broad energy spectrum and it is not possible, or it becomes difficult to limit the wavelength which is necessary for treatment of psoriasis. And vigorous exposure to sunlight may lead to sunburns also. So modern phototherapy, which began in 1895, when Niels Rydberg Finsen, who is also known as the father of modern phototherapy, he treated lupus vulgaris using a carbon arc lamp. He had also received Nobel Prize in dermatology, which is the only one given till now. The modern age of phototherapy utilizes narrow band UVB light due to enhanced effectiveness and safety, as it matches the therapeutic action spectrum of psoriasis, which is near in the region 311 to 313 nanometer. So regular exposure of the affected skin to this light under medical supervision help impede the cell growth, suppress immune activity, and provide solace in skin irritation. With various treatment modalities available, phototherapy remains the efficient and safe treatment for psoriasis owing to its low cost and lesser side effects. That is, the erythromal or the sunburns are seen less when you are using phototherapy for psoriasis. Out of that, gadolinium with emission near 313 nanometer, this rare earth bears immense potential for application in phototherapy lamps utilized for the treatment of psoriasis. Here I'll discuss about the potential of BA-B8O3 phosphor, which has been activated by gadolinium, and how it is useful for psoriasis treatment. To find out its efficiency, the photoluminescence study was carried out. Here we can see two figures. The first figure is about the excitation spectrum of the phosphor, BA-B8O13, and second is its emission spectrum. As GD3 plus is doped in this phosphor, GD3 plus, we know that it has FF transitions with 8s7/2 as its ground state and 6p, 6d, 6i as its excited states. So seeing in the first figure, we can see the peak. It is an excitation peak. The excitation peak we can see over here. There are four peaks. One is at 246, the other 252, 274 and 278 nanometer. So using these peaks, this is the prominent one, that is 274. So we can excite the phosphor at this prominent peak in order to get maximum intensity in emission. These four peaks, they are due to the one at 246 nanometer is due to 8s7/2, 6d7/2 transition of gadolinium. The next at 252 nanometer is on account of 8s7/2, 6d9/2 transition. The third, the dominant one, is due to 8s7/2, 6i17/2 transition of gadolinium, and the 278 nanometer peak is due to the transition of 8s7/2, 6i11/2 transitions of gadolinium. So we excited the phosphor at the dominant, yes?
Excuse me, yeah, welcome, ma'am. Try to conclude within 1 minute.
Yes, sir, only one slide left. So when this phosphor was excited at 274 nanometer, it was found that a good peak at 314 nanometer was seen, and the optimum concentration of gadolinium, which gave the maximum intensity, was 0.2 mole percent. So 0.2 mole percent of gadolinium gave an intense peak at 314 nanometer, which is used for the treatment of psoriasis. But since gadolinium has FF transitions, these peaks are weak, means they give less intensity. So they were doped with a they were doped with a sensitizer. Where the sensitizer is presmodium. On presmodium doping, we see that the excitation peak has two peaks. One it has 274 due to gadolinium, and the other is as 220 nanometer, which is because of presmodium. This presmodium absorbs the incident radiation, incident energy, and it gives it to the gadolinium. So on doing so, on excitation at 220 nanometer, we got again the peak in the same region, but now at 313 nanometer, and this peak was found twice intense than that of the gadolinium only when gadolinium was doped. So plasmodium acted as a sensitizer which transferred its energy efficiently to gadolinium. And so we can say that this phosphor has the potential to be used in phototherapy lamps for the treatment of psoriasis. Thank you.
Thank you very much, ma'am, for uh, giving the brief of gadolinium dope phosphor for phototherapy applications. Thank you very much.
Thank you, sir.
Mangoli, sir. So Dr. Amol Nande is here, so I'll request Dr. Amol Nande to make his presentation.
Yeah, sure. Thank you very much, sir. Just I'm looking for how to share my screen because someone is presenting.
No.
So
You can share. You can share.
yeah, but there is a find device, but I cannot see. Yeah, now it is shared. Yeah. All right.
Okay.
Oh yeah. Yeah. So my screen is visible now, isn't it?
Yes.
Yeah. All right. So
Yes, it is visible now.
today, actually, I am going to deal with some new approach of synthesizing silver nanoparticles, and in this conference, we are presenting a review paper on it. We have already published a couple of papers and a review on this topic. So before going in detail, I would like to introduce myself. I am Dr. Amol Nande. I am working as an assistant professor at Guru Nanak College of Science, Ballarpur. So start with why we chose silver to be reduced to nanoparticle size. So everyone does know that silver is one of the most studied nanoparticles in different approaches because of their unlimited of biochemical and biomedical application like antibacterial activities, antifungal activities, antioxidant activities, anti-cancer activities. Apart from that, it has high thermal and electrical conductivity, and it's again useful in all household devices as well as optical sensor, drugs, and food industry. So that's why we were chose, to confine down our literature review about over silver nanoparticles. And it is more interesting to see that when we reduce silver nanoparticles or when we reduce bulk silver to the nano size, it shows unique property, and this property changes with their shape. So if silver and gold, if you see the different nanoparticle size, so you can see they scatter different light, different color of light. So that's the beauty about these two metals, although this is noble and everything, but still it is very fascinating to study or to put up all the data together. The second question would arise why we choose green approach. Because already there are two famous approach, chemical and physical approaches are there to synthesize any metal nanoparticle. So what does green approach or bio approach makes it different? So green synthesis actually, as I said before, so silver nanoparticle or any metal nanoparticle, we can synthesize using physical, chemical, and biological approach. But physical and chemical means if you want to use sputtering technique, so sputtering technique itself costs you around more than 25 lakhs, and to start up and to put down in more pressure and everything, you need different kinds of noble or how can you say like gases like helium. If you want to make oxide, then you need oxygen gases. So physical method is very costly. The another approach is chemical approach, but again chemical approach deals with very poisonous chemicals. These are not good for human health, like oxalic acid, NaH, BO4. So these kind of things are very harmful to environment and human body also.
So for biomedical approaches, it is very difficult to go with both. Biomedical application, it is very difficult to go with both approaches. So there is third approaches now taking into picture, that is we term as a biological approach or green approach. So the beauty about this approach is it is very simple process. You can make nanoparticles within 4 to 5 hours at any condition. Those are non-toxic because the whatever reducing agent you are using, those are used with either taking it from environmental extract or some plant extract, and uh, it is like dependable. You can do anything. Yeah. On top of that, it produces very high yield, so the quantity is very good. Then solubility is good, and you don't need any extra stabilizing agent to stabilize the nanoparticles. That's why everyone is like moving around green synthesis. Then the next would be like why. So if you want to do green synthesis, which kind of things you can use? The most famous reducing agent or material used in green synthesis are plant extracts. So you can just take any part of your plant, any plant, and like root, leaf, flower, fruit, seed, stem, bark, whatever you can take, convert that into extract, and you can use it as a reducing agent in your chemical reaction, co-precipitation method, and you will get the nanoparticles. The another thing is instead of plant extract, you can go for fungus extract, microorganism, as well as sea animal or seafood waste. So these are like another three different ways to synthesize these nanoparticles using green approach. But again, fungus and microorganism is little bit risky to deal with that. That's why our world is roaming around to synthesize nanoparticles using plant extract. So it is very simple. You take that reducing agent, mix the solution. If you want to take, for example, here we are making silver nanoparticles. That's why we take silver nitrate solution, mix with plant extract, heat for a while, continuous stirring, and then it changes its color from light brown to the dark brown. So if you see this kind of changes, that means your chemical reduction reaction is happened, and there are the synthesis of your silver nanoparticle. So this can be confirmed easily whether there is a silver or any other material. This can be confirmed by very basic tool like XRD. This is clearly a silver nanoparticle synthesized using neem leaves, and you can see there is the strongest peak of all over silver all over there. So this confirm that it is possible that to make nanoparticles using green approach. But except from X-ray also it is very difficult to see that whether the nanoparticles are formed or not. That's why we took TM images and SM images of those, where you can see the scale is around 50 nanometer. So all our nanoparticles are in the range of 10 to 20 nanometer. So and even XRD data is sorry the set data confirm that the all structures are very crystalline and uniform size. Uh, so concluding remarks. So it is very easy method to make silver nanoparticle, and anyone can try in any kind of lab. They just need couple of tree leaves or something from tree or any other living organism extract, and then you can put the metal salt solution in it, heat it for a while, you will get this nanoparticle. And this nanoparticle is widely used. Literature clearly shows that all these nanoparticles are widely used in all kind of application like biomedical application, pharmaceutical application, and cosmetic application. And why it is like used in all these applications? Because the residues coming out with these nanoparticles are completely adopted or adjusted by our body. So it is not hazardous to human body or any other body, like the heavy chemicals extract or heavy chemicals residues left out during chemical process. So I guess it is going to be like one of the outstanding process to synthesize nanoparticle. And in our field, there are many medicinal plants, so we can go around and start working on it. And I guess that would be more useful. I finish it with this slide. Thank you very much for providing opportunities. If you have any question, you are free to ask. Thank you.
Thank you, Dr. Amol, for making such a nice presentation. Thank you
sir.
very much. Any questions? I think no. So now we are heading towards the another presentation. HB Meshram sir is available here. So I request HB Meshram sir to make his presentation. Hemant Kumar Meshram sir. Meshram sir, am I audible? Meshram sir. Hello, Meshram sir.
Mangode sir, Meshram sir is not there.
Sir,
I think he is facing some problem. He's trying to unmute, but I think he's facing some problem. We'll try again. Meshram sir, now you can speak. I think you can increase the volume. Try to increase the volume of your device. Meshram sir. Okay. Till then we'll move towards another. Am I audible, sir? Meshram sir? Okay. We'll move towards next presentation. Dr. Ishita Ghosh ma'am is here. So I request Ishita Ghosh ma'am to make her presentation. Sunil, unmute Ishita Ghosh ma'am. Attendee.
Yes, sir. Yes.
Hello,
Ma'am.
am I
You are
audible?
audible, ma'am. Yeah, you are audible, ma'am.
Please share my PPT.
Yes, ma'am. Now you can make your presentation.
Okay, good afternoon, everybody, and thank you all for giving me an opportunity to present myself in the international conference on advances in physics. So, my topic is the emerging scenario with quantum computing. As you must all know, this is really a catchword of the session. Those who are physicists can very well associate with this word because this is really a word that is doing the rounds nowadays. Okay, next. So, let's see what is quantum computing. So how it came into existence? Let us just see a brief thing how it came into existence. It started in 1982 with the famous scientist Richard Feynman. He introduced this word quantum computing, and by then, successively through the years, it is going on. It is going on improving itself, and though there are steps in which there were failures, you can see the years are mentioned over there in which quantum computing has slowly and slowly gained ground. And you can see by 2010, D-Wave first commercial quantum computer with 128 qubits has come into being. So let's see what's special about quantum computing. Next slide, please. Okay, basics of quantum computing. before quantum computing also computing did exist, and it was by classical bit. So what's the classical bit? It is 0 and 1, as you all know, by which we compute off state and on state, or rather it is called 0 and 1. But what's special about qubit? Qubit is 0 and 1 both. So that's the difference, and that is where everything has worked out differently. So that's called a qubit, in which 0 and 1, both the states are present simultaneously. There's no single existence of 0 or 1. It is superposed states of 0 and 1. So how does a quantum computer work? It does not work like, obviously it does not work like a regular computer, and you can see very well that this quantum computing works with the help of quantum bits, rather it is called qubits. So it's a combination of 1 and 2, 1 and 0, as I told, and the basic thing is that it is a superposed state of 0 and 1, so it can stay in 0 state or 1 state, both simultaneously. Next please. So how this qubit works? As you all know, the electron has a spin, up spin, down spin. These are the very basic things in which though two types of spin are found in every electron. In the up spin, the energy is in the low energy state, whereas in the down state, it is in the high energy state. And this is how when qubit is introduced, you see there are both states simultaneously, and accordingly it aligns itself with the magnetic field, and hence an entanglement takes place due to this property of qubit to exist in a superposed state. Next please. Next please. Okay, so what one previous slide please. So this is how this is classical versus quantum. So classical was what we were doing and how it increased and developed itself. But you now see that with the quantum computing coming into existence, it's gradually increasing. So why is quantum different? I have put here more, analyzed it in more details. You see two catchwords are there in quantum computing. One is superposition of qubits and the other is quantum entanglement. Now what is this entanglement? In entanglement, you cannot independently find any state without the existence of the other states. Even if the particles are separated at a large distance, you see that they will entangled with each other. Their state cannot be described independently of each other. So as you see, classical state and quantum state, this is the basic things. The qubits, they superpose with each other. As a result, the final result, the final measurement, it can be either 0 or 1, existence of both simultaneously, and also the quantum entanglement, in which the group or the pair of particles generated do not exist independently. Even they are separated by large distance. Even if they are separated by large distance, they are entangled with each other. Their properties are entangled with each other, and these two things are utilized to do the work that is called quantum computing. Next please. So this is the difference between classical and classical and quantum computing. We are gradually growing up and we are trying to increase. Now what is happening is that, as you can see the years written below in the quantum computing graph, there successively the years are passing on, and what is now being done is that number of qubits are gradually going on increasing, so that the powers, the rate, the efficiency, the power storage, the information storage, all of those are increasing, and year by year we are trying to develop on the number of qubits to be involved in the process of quantum computing. Next please. So what are the merits of quantum computing over classical computing? So these are the few basic points in which it is beneficial. What is that? First of all, first and foremost that we are looking to is that larger sets of data can be quickly evaluated. Means the efficiency of these quantum computers will be more than the classical computers. Then operations are reversible as long as the resulting states are intact, because I told you about the superposition and the qubit form in which they can exist both in 0 and form, so they are reversible. Moreover, quantum computers are thought to be much smaller in size than the similar capacity classical computers. Also, the storage capacity is large because what happens is that it is 2 to the power n qubits. Like 3 qubits, if you have only 3 qubits, the it goes to 2 to the power 3, that's 8. So it has an enormous storage capacity. It can multitask itself, and security features are also unbreakable, the one which is looking into, and power consumption is also reduced, and it can solve some unsolvable problems. These are the thought of merits of quantum computing. And obviously anything which has merits will have demerits. Look into the demerits. Next please. These are the demerits. So you can see quantum particles, they are quite they're quite active, and it's quite difficult to control it. And the most important fact that is there, lots of heat are generated. So to control the heat and the temperature, it is difficult, because lots of energy and lots of I mean resources will be involved in making it cool and giving it a quantum computing. Also, it is quite difficult to create large scale quantum computers. And also you can see the need of noise free and cool environment is a must. Complex hardware schemes are also there. Decoherence or loss of information from the system into the environment is also there. So these are the demerits. You saw the merits, you saw the demerits. And thus you can see that it's not all the fun game, and it's not all over, and it's all not one. But there are merits as well as demerits in quantum computing, but people are seeking after it to gain some quite of advantage in time, in terms of storage, in terms of speed, in terms of greater efficiency. Next. Next please. So where sorry, applications slide please. Okay, anyway, status of
Ma'am, try to conclude.
hi, just a minute, I will conclude. So these are the applications of quantum computing. You can very well see these are the various fields which are thought out to work by the application of quantum computing. And if quantum computing works as it is working very well, we can see these applications of quantum computing. Next please. This is the status, and you can see how great deal of energy, great deal of money, great deal of thoughts are being put into the quantum computing world, and the things are increasing year by year, day by day, and the things, and we hope for a better use of quantum computing. Next please. Next please. So these are the 20 years of quantum computing, and as you can see, there's a rush, and this is also accumulation of the status of India. We are also not far behind, and we have started the process of quantum computing in India, and these are the various packages and projects which are into being to give a speed up to quantum computing. Next please. These are again some more facts about the present status, and as you can see, 8,000 crore plan is there for the dream quantum computing project, and we hope that India will also be in line with other big countries to get a kick off quantum computing. Next. All the basic organizations have joined up and lined up to do the things. So this is the future of quantum computing, and we hope that we will have quantum computing. But again, there's a word of caution for everybody over out here, that quantum computing cannot be done all alone. Classical computing will stay and is there to stay. Quantum computing will only just be a subsidiary, be a supplement to the classical computing to use it wherever necessary and increase the efficiency. Next please. I hope that's all from my side. These are again some things which are 10-year forecast and future of quantum computing. So that's the conclusion. It is a radical change in the way computation is done. Basic advantages lie because we use the facts of quantum mechanics, the basics of quantum mechanics, and classical computers will significantly be larger. And so what's in future, I hope, is that there will be a mix of classical and quantum computers, and we are ready to see what the future has in store for you. Thank you all. Thank you for giving me a chance.
Thank you very much, ma'am, for taking us to a very fascinating uh, area of quantum computing. Yeah,
Thank you,
really
sir. Thank
going
you.
to change the world around us, and it will, what we can say, it will do the work which will take several years for a conventional computer. So thank you once again.
Thank you, sir.
Now
Thank you.
we'll move towards the next participant, that is Dr. S. Venkataramanna Reddy. Reddy sir, am I audible? Reddy
Yes.
sir.
Yes.
So you are now
I'm
the presenter. You can make your
speaking.
presentation.
Is it visible, sir?
Yes,
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 it is
yes.
visible, sir.
Okay. I will start my presentation now. Big models for atmospheric data. That is the title of the paper. Actually, I am Dr. S. Venkataraman Reddy, Assistant Professor, Department of Physics, SVA University, Tirupati. Uh, Hello.
Sir, you are audible.
Okay. Here we're discussing about atmosphere. Atmosphere, there are a number of variables. That variables are rainfall, temperature, wind speed, humidity, visibility, wind gust, precipitation, etc. For that variables, we take wind speed. Uh, that is for estimation of wind speed by taking temperature, time, and visibility using the Gaussian process, RBF network, A star, and additive regression. First one, Gaussian process. Gaussian process is simple and general class of probability distribution on functions. Gaussian process has been used from 1970s in geostatistics and meteorology. Fringing was used for prediction of geostatistics using Gaussian process and using a probability based function. Bayesian process is free from regression. Bayesian inference can be used to make predicts from data. That is a P of probability of FD equal to P of D by F multiplied by P of A by P of D. Our next one, RBF network, radial basis function network, is an artificial neural network that utilizes a radial basis function as activation function. The output of the neural network is a linear combination of radial basis of the input function and neuron parameters. RBF network have three layers. First layer contains input. Second layer is a radial basis function, and final layer is output that we can observe in the figure. So at the bottom we can observe the input, uh, at the middle radial basis function, and at the last we can get the output. Next, K-star algorithm. K-star was developed in 2009 by Hossein Aljijar for finding the K shortest paths between a designated pair of vertices in a given directed weighted graphs. K-star does not require the graph to be explicitly available and stored in memory. K-star is mainly based on heuristic functions. Next, additive regression algorithm. In general, additive regression algorithm is yi equal to b0 plus b1 xi plus ei, where yi is dependent variable, ei is error variable, b0 is intercept of a regression line, b1 is a slope of a regression line. These are the four methods or techniques or models. Next, what we are doing. That is empirical investigations. By taking wind speed as dependent variable and the time according to data day wise, that is from 1/1/2017 to 1/1/2019, that is 2 years data. Minimum temperature, maximum temperature, visibility as independent variables. We perform cross validation as a test mode in Vika software. Radial basis function network, that is the RBF network. Here, linear regression model, that is the visibility equal to 0.355 plus P cluster plus 0.3548 multiplied by P cluster plus 1.3. So when we run the Vika software for the RBF model, we take the certain time, that is only 0.5 seconds, and from there we can get the correlation coefficient, mean absolute error, root mean square error, relative absolute error, root relative square error, total number of instances 725, ignored plus unknown instances 6. So here we explained about the number of parameters we can get from the Vika software when using the radial basis function network. Similarly, we run the other three models, that is the K-star network, Gaussian processor, and the last one, additive regression. When we run that three, similarly we can get all the parameters, and when after here RMSE, root mean square error, and uh, uh, another parameter. So here that is a that explained here for the intraday data, that is wind speed, maximum temperature, minimum temperature, visibility, and time. Wind speed is independent variable, and all other four independent variables. We performed radial basis function network, K-star algorithm, additive regression, and a Gaussian process by using tenfold cross validation using the Vika software. And When comparing all the four, we get the best model. So best among the models, that the four models is chosen using root mean square error and mean absolute error criteria, and that are summarized in the table. So RBF network, when we observe the RBF network for that model, RMAC value 0.3333 and mean absolute error that we can observe. So for the K star, for the additive regression, Gaussian process. So for the four models, we have the RMAC and MEE. So when observing that values, we can say that the minimum RMAC, root mean square error value, is for the Gaussian process model. So we say that for which model the RMAC is minimum, that model is the best model compared to the other models. Thank you for the organizers for giving the opportunity to present my work.
Thank you very much, sir, for explaining VECA model.
Thank you, sir.
Now we'll heading towards our next participants, that is Dr. R.G. Vidate. Okay. Vidate, sir, am I audible?
Hello, I'm ready.
Am I audible? Okay, 1 minute. We'll take to you on panel list. You are audible, but your sound is very slow. Sunil? Sunil, sir? Sunil, sir? Am I audible? One minute, sir. I think there is some technical error. Sir, you can make your presentation. Hello? Sunil? Sir. विदाते सरांना पॅनलवर घे ना, अटेंडी मध्ये पण एक आहे त्यांचं, मला वाटतं लॅपटॉपवर असतील ते. नाही, इथे आहेत पण ते मोबाईलवर आहेत कदाचित. पॅनल लिस्ट मध्ये आहेत एक लॅपटॉप आपल्या अटेंडी मध्ये आहेत, त्यांना पॅनल मध्ये. ओके. विदाते सर, एम आय ऑडिबल नाउ? Hello, Vidate sir. Vidate sir, you can make your presentation now.
Start.
Okay, it is visible now. Yeah, your PPT is visible. Now you can make your presentation. And you have 5 minutes, sir.
Yes, thank you, sir.
Okay, good afternoon, everybody.
Good afternoon. Good afternoon.
Plan of presentation. My title is Structural Properties of Vanadium Substituted Yttrium Iron Garnet. Presentation, Introduction to Ferrite, Literature Survey and aim of the present work, Presentation Method and Experimental Techniques, session on Y3 VXAP5-X O12 for sample 0.0, 0.2 and 0.4. Ferrites are complex magnetic oxides that contains ferric oxides Fe2O3 as their main component and metal oxides. Ferrite possesses both electrical as well as magnetic properties, hence it is commercial important magnetic material. On the basis of crystallographic aspects, the ferrites are classified into major types: the cubic ferrites of spinel type, the cubic ferrites of garnet type, and hexagonal ferrites. Crystal structure of spinel ferrite possess lattices, tetrahedral A site, octahedral B site, and the structure of garnet possesses 3 sides. The first is tetrahedral D site, octahedral A site, and dodecahedral C site. There are many more applications of this material in the optical isolator, optical switches, tune oscillator, multiplexer, magnetic field sensor, band reject filter, and fiber optic sensor. Literature survey. The study of yttrium iron garnet for the magnetic material structural properties have been reported in the literature. The use of non-conventional methods such as sol-gel, thermal deposition, wet chemical co-precipitation been reported for the preparation of nanoparticles. The structural, electrical, dielectric and magnetic properties of vanadium substituted yttrium iron garnet are not reported in the literature. The aim of the present work is to prepare vanadium substituted yttrium iron garnet system Y3Fe5-X, Y3Fe5-X VX O12 standard solid state reaction to investigate the effect of vanadium substituted yttrium iron garnet. There are many more methods as like sol-gel method, precursor method, combustion synthesis, spray pyrolysis technique, chemical bath deposition technique, and wet chemical co-precipitation method. This flow chart shows the ceramic method preparation of material by using this ceramic method. Firstly, calculation of constituent oxides, then weighing and mixing, grinding for 3 hours, pre-sintering for 1200 degrees Celsius, then grinding for 2 hours. Sintering is provided for 1350 degrees Celsius, and then binder is added and material is in the pallet form. Removal of binder by using the heat, and then final garnet is formed in the form of Fe3O12. Then experimental technique. After that, in the present work, the prepared samples of the Y3 VXAP5-X O12 for X is equal to 0.0, 0.2 and 0.4 were characterized by the following experimental techniques. X-ray is taken in between 2 theta, in between 20 degree to 80 degree. Target is used as CUK alpha. Lambda is 1.5406 angstrom. The model Philips PW3710 is used and the scanning rate is 1 degree per minute. The IR of the spectra of all samples IR of the spectra of all the samples of the present samples were recorded at room temperature in the range 300 centimeter per to 800 per centimeter. Model Perkin-Elmer spectrometer 783 is used. This graph shows the X-ray diffraction for 0.0, 0.2, 0.4. The analysis of X-ray diffraction pattern reveals that the samples under investigation possesses single-phase cubic garnet structure for these samples. This graph shows the lattice constant and goes on in. Next, the X-ray density goes on decreases with composition X. Shows the HKL interplanar spacing D of a Y3 VXFE5 minus 412 for these samples 0.0, 0.2 and 0.4. This table shows X-ray density, bulk density, porosity, and particle size of Y3 VXFE5 minus 612. From this table, we can observe that lattice constant goes on increases from 12.364 to 12.381. The X-ray density can be shown in this table. The same way, the particle size is listed in this table. It shows IR spectra of Y3 VXFE5 minus X O12 of samples of a given sample for these three samples 0.0, 0.4 and 0. Shows typical absorption bands indicating the garnet nature of samples. It is reveals that broadband nu2 appears at around 400 per centimeter and 600 per centimeter, assignable to the stretching mode of the tetrahedral in the yttrium iron garnet. IR bands at 655 per centimeter, 605 per centimeter assigned to new per modes, whereas the bands at 397 per centimeter and 424 per centimeter can be assigned to a new modes. It indicates that the crystallization of samples is more complete. This table shows the vibrational band frequency of Y3 VXFE5 minus X O12 for these samples 0.0 to 0.4, and we can observe from this table using ceramic technique P5 minus X O12 are successfully prepared. The single phase cubic garnet structure of the prepared sample of Y3P5 minus X VXO12 was confirmed by X-ray diffraction analysis. The lattice constant found to be increased with vanadium substitution.
Thank you very much, sir, for nicely explaining the synthesis and characterization of vanadium substituted yttrium iron garnet. Now, I think Priyanka Bhoyer ma'am, Priyanka Bhoyer ma'am is also available. Sunil? Yes. Bhoyer ma'am is in, I think, So, Now I request Priyanka Bhaur ma'am to make her presentation.
Yeah, thank you, sir. I'll share my PPTs now. My PPTs are layout.
It is visible, but rotate it.
Yeah,
Ma'am.
it is visible, but it is up. Okay, let me do it one more time. Yeah, now it's fine. Is it fine now?
Yes, it is fine.
Okay, so good afternoon, everyone. I am Priyanka Boyer from State Kestriwal Purval College, Kamti.
Ma'am, you have 5 minutes to conclude your presentation.
Yeah, thanks. So the topic of my presentation is robustness of directed percolation under relaxation of prerequisites, the role of quenched disorder. Directed percolation universality class is a university class of non-equilibrium phase transitions from active phase to absorbing phase. And absorbing state is a state which system cannot escape. And this universality class is characterized by universal exponents. And the models that fall under this universality class ranges from epidemic spreading models, spreading of forest fire disease models, transport of disorder, transport of substance in disordered media. However, although this class is found very much in theoretical, the experiments, this universality class is not found, and it can be attributed to inevitable noise, inhomogeneity, and disorder that are present in an experimental setup. So what we did in this paper is we introduce a mixed model. So we take a 1D lattice and divide it into two types of site, A and B. Both sites are governed by different set of dynamic rules. So basically, one types of we have done a contact process. So basically, contact process can be any disease model can be easily put into contact process. So one type of site recovers in one time step, whereas all the other types of site recovers in some tau time steps. So this is basically our idea of introducing inhomogeneity in the lattice. So we find that in presence of small random spatial inhomogeneity, it leads to no change in the critical behavior of the system. The dynamics of the system approaching towards absorbing phase, it belongs to the directed percolation universality class. And we established this by comparing the critical exponents of this model with the critical exponents of deep universality class, which are universal in nature. So for this, we evaluate the order parameters. Order parameter is basically the number of, for example, if 1D lattice represents a number, so for example, 1D lattice represents a set of healthy and infected individuals. Then our order parameter rho of T is the set of infected individuals. So we have plotted in infected individual versus time on a log scale for tau equal to 1. So the recovery time is 1 for type A sites, and this is basically for tau equal to 1. So type A sites are just the same as type B sites, and we see that the order parameter varies as 1 over t to the power 0.159, where this delta, which is equal to 0.159, if this is close to the value obtained for the dp, which is 0.1596. So we can see the power law, nature of power law, for all the probabilities, all the infection probabilities above the critical probability, which falls at 0.7055, the number of infected individuals saturates, whereas if the infection probability is less than 0.7055, then the number of infected individuals after some time, it definitely goes to 0. So the similar nature of DP is observed for tau equal to 2. So type A sites, this is for type A sites. Type A sites also show power law behavior with delta is equal to 0.159. For P greater than PC, we have saturation, and for P less than PC, disease extinct. So this power law which we are observing here is ubiquitous in nature, and it is observed for all the DP models. This is for type B sites where our recovery time is 2. After 2 time steps, an individual recovers. So this is a small defect, and defects are relevant for DP universality class. This is for type B. For type B, the number of infected individuals, again it shows power law with this delta is equal to 0.153, and above the critical point is again same for tau equal to 2 also. For all PCs above 0.7055, the disease saturates, whereas for infection probability is less than 0.7055, the disease goes to extinction. We evaluate another quantity which is called local persistence. So although the exponents given by local persistence, which is represented as theta, which is represented as theta, it is not universal in nature, but it is useful in calculating other parameters such as nu parallel, which is universal in nature. So here we see that at the critical point, below the critical point, so basically persistence is for how much time the individual retain its initial condition. So that is the persistence. So persistence will saturate for all the infection probabilities less than PC, and for all the infection probabilities greater than PC, persistence will go to 0. So the same nature we have obtained for A types of site, and the same nature is obtained for B types of site. And we try to find the Z scaling of local persistence. So this will give us the dynamic exponent Z and the persistent exponent theta. So persistent exponent theta is found to be 1.475 in this case, which is equal to 1.49 for DP universality class, and Z is equal to 2, so it falls in the subdiffusive region. So here what we have done, we have evaluated the a lattice size of 20, 40, 80, 160 and 320, and based on the values that we have got, we tried to simulate the values of Z and theta, and our obtained values of Z and theta are close to that for that of DP model. Similarly, we have done the same analysis for type B sites which recover after tau equal to 2 time steps. Here we have taken the lattice size of 80, 160, 320, 640 and 1280. And here we have obtained the value of, here although the value of theta has changed, so the persistent exponent has changed, it is equal to 0.27, but the system remains in, has the same dynamic exponent Z equal to 2. So this persistent exponent, because it is not a universal phenomena, so because these exponents are not universal in nature, unlike Z, nu, parallel or delta, these are universal in nature. Theta is not universal in nature, but it remains in subdiffusive region, so it belongs to DP universality class. Similarly, we try to find out the nu parallel scaling for type A sites and type B sites. So here what we do, we analyze the system for P greater than PC for the same size of as we have taken in the initial condition, and we try to plot a graph between the persistence of the system into P minus PC times mu parallel theta, where theta is the persistence exponent, and we have found the collapsing nature of all the three graphs, and the obtained value of mu parallel is 1.73 and obtained value of mu parallel for DP class is 1.732. Similarly, theta is 1.491, which is close to that for the DP.
Excuse me, ma'am. Try to conclude within 1 minute.
Yeah, I have finished. This is my last slide. And here in the second type of sites, mu is equal to mu parallel is 1.32 and theta is 0.27, I think. So again, because persistence is not persistent exponent is not a universal criteria for DP, but mu parallel and ZR. So we conclude that this remains in DP universality class, and with introduction of small impurity, small disorder, the system remains in DP class only. Thank you.
Thank you very much, ma'am, for presenting your research work on robustness of directed percolation under relaxation of prerequisites, role of quench disorder. Thank you very much. Now we are heading towards our next presenter, Saud Alwalidi. Sunil?
Yes, sir.
अटेंडी मध्ये आहेत सर, त्यांना इकडे प्रेझेंटिंग मध्ये देतो.
ओके. हो, येस सर.
आणि कागे सरांकडे आहे मला वाटते प्रेझेंटेशन.
Yes.
So, Dr. Saud, you can make your presentation now.
Thank you, sir. Good afternoon, all of you. My name is Saud Al-Walidi. I am from Yemen, and I want today share with you my presentation under the topic. Please, sir, can you display my PPT? Hello, sir. Yes, thank you. Okay, can you start now? Okay, thank you, sir. Okay, today I want to share with you my presentation under the topic of study of some polymers using dielectric spectroscopy. Next, please. Hello, sir. Please, next slide.
Next.
Hello.
Yes, ma'am. Just continue. You are all.
Okay, but PPT it is not going.
Kage sir, next slide.
Next slide, please. Because only 5 minutes, I won't do fast.
Continue.
Because I don't see my PPT, so how can I? Because it
is visible, ma'am. It is experimental method.
Okay. How can I can explain now?
Yeah, you can explain now. Is it visible to you?
Okay, I will only 1 minute. Okay, my topic is study of some polymers using dielectric spectroscopy. My content is first bound is time diamond reflectometer experimental techniques and dielectric theories and result and discussion. Last one conclusion. Aims and objectives. Okay. Next slide, please, sir. Aims and objectives. The first objectives is to study structure and dynamical properties of polyethylene glycols and to determine dielectric parameters such as dielectric constant, relaxation time, and thermodynamic properties such as entropy and enthalpy, last one, free energy, by using time diamond reflectometer technique in the frequency range of 10 megahertz to 20 gigahertz at different temperature and chain length. Experimental method, next slide please. The complex permittivity spectra was obtained by using time diamond reflectometer technique use. This is instrument I use for my experiment. So next slide, I will show this. Next slide, please. I will show this experimental setup of TDR. Next, please. Next slide. This is experimental setup of TDR. It is there is the three parts. The first part is sample holder, and second one, no, please again. This is experimental setup of TDR, and also there is sampling oscilloscope. Okay, and this is TDR with. Okay, next slide. Okay, this is TDR we formed for reflected pulses with symbol and without symbol, and this is spectrum for add and subtracted pulses. Next one is reflection coefficient. We can calculate reflection coefficient spectra by next slide, please. By using this equation, we can calculate reflection coefficient spectra, and next slide, we can calculate complex permittivity spectra by using this equation. The first one, it is epsilon dash. It is measure of how much energy from the external electric field is stored in the material, and the epsilon double dash is how much the energy from the electric field is lost. Next slide. The dielectric measurement, we can use Havrilke-Nejmi equation is used for calculate complex permittivity spectra by using this equation. Next slide, thermodynamic properties. The thermodynamic properties can be calculated by using this iron equation. Okay, now this second slide. This is structure of polyethylene glycol, and this is monoethylene glycol, and the second one polyethylene glycol. This structure, and polymer is nothing, only is substance of material consistent of very large molecular or micromolecular compounds of many repeating subunit, means monomers. And second slide, please. It is permittivity spectra. This is spectra between the dielectric constant and also log of frequency in gigahertz, and dielectric loss with log frequency gigahertz at different molecular weight and at different temperature. We select this in 25 temperature in 25 degree. Okay, second slide. It is call plot of BEG 200 and 300, 400 and 600 at 25 temperature between dielectric constant and dielectric loss. Second slide. It is between dielectric constant and temperature. We see that when temperature is decreases, the dielectric constant is increases. That because the intermolecular interaction, it is increases when temperature is decreases and at different molecular weight. Okay, second slide. Next slide. It is this spectrum between polymerization and dielectric constant, and we see that when polymerization is increases, it is clear that dielectric constant is decreases. This is last next slide, because no time. It is relaxation time. We see that the time doesn't increases linearly, with increases the molar chain length. Okay, and last one. It is free energy. we see that the free energy is very close to range between 4 and 5 kilocalorie mole, and this activation energy needed for breakage of hydrogen bonds, and the free energy of activation is found almost independent of temperature of respective system under study. Last one, conclusion. The dielectric relaxation parameters of polyethylene glycol for different polymerization have been studied by using TDR, and the static permittivity for low molecular weight BEG is found to be greater than the value of static permittivity of higher molecular weight polymer at all the major temperature values, and the free energy of activation is found almost independent of temperature of respective system under study. The average value of entropy is found to be negative for BEG 300 and will be negative for 200, 400, and 600. Thank you for everyone.
Thank you, ma'am, for sharing your work on polymers and their characterization using dielectric spectroscopy. Okay, thank you very much. Now we are heading toward our next participant, that is Mrinmoy Garai, ma'am. I don't know, ma'am, or okay, Mrinmoy Garai, ma'am.
Yes, I am here. Please, yes, thank you. Yes. Am I? Hello?
Yes.
Yes. Good afternoon, everybody. Myself, Mrinmoy Garai, will share my current research work related and thermal stability of silver and gold nanoparticle doped mica glass ceramic sealant for solid oxide fuel cell application. Here in the left side of the slide, you can see solid oxide fuel cell is an efficient energy producing device which electrochemically converts the electrical energy, chemical energy of a fuel into the electrical energy. Here the water is the byproduct with releasing two number of electrons, which in a circuit gives producing the energy. But this energy producing device requires a high temperature sealing material, which should maintain the gas tightness between the anode and cathode to avoid the intermixing of fuel and oxidant at very high operating temperature. That I mentioned, it is 800 to 900 degrees Celsius. Moreover, it should be chemically non-reactive and it should possess thermal recyclability at high operation temperature. So this type of sealing material is thermally stable at high temperature. So if you use a gum like any other sealant or like polymer, then it should evaporate at around 200-300 degrees Celsius. So glass is a kind of sealing material which exists at certain higher temperature like 800 degrees Celsius. Here you can see this is the design of the glass system, and after heat treatment at the operating temperature like 950 degrees Celsius, it is converted into mica kind of glass ceramic, and this glass ceramic is used as a sealing material. But glass to glass ceramic conversion is a typical heat treatment phenomena. But there, for generating this particular crystalline phase, we need some nucleating agent which facilitates the nucleation phenomena. Here we have added silver and gold nanoparticles. I will show how these nanoparticles will help for the phase separation. That means the crystallization to this particular phase. And this particular phase is important because you can see the layered crystalline structure here. This layered crystalline structure can offer a high thermal expansion value. And the high thermal expansion value is required because the solid oxide fuel cell other materials are having thermal expansion value very high. So if the sealing material is not having the thermal expansion value compatible, then thermal crack can arise. So the sealing material should also have the thermal expansion value comparable with other materials. Here you can see this is the base glass composition. Here as nucleation capability, we have added silver and gold nanoparticles. This is 0.2 weight percentage. But the technique to add the nanometals in the glass is a very typical one, because one electrochemical cell we have to produce, because silver and gold nanometal we cannot directly use. We have to add as their salt. Here we have added silver nitrate and auric chloride. So silver nitrate is Ag plus and auric chloride is Au3 plus. So this should be reduced, and we should have used and reducing agent. Here we have added stannous oxide, SNO. So SN2 will be reduced to SN. This is 2 electrons. So this is the electrochemical potential, and they have the electrochemical potential for these cells. From there we can get the free energy value, that is minus NFE. This is Faraday. So from this we have calculated the free energy is negative for these two cells, and that's why we have added the silver and gold nanoparticles as their salts for the particular ratio. This is 0.2, 0.2, and this is in situ doping, means from their salt. This is ex situ doping. This is another technique. Directly we add their nanometals. Here other metals are there. They can they have the capability for nucleation. Here in this journal, in we have shown this zirconia J.4 plus. It is also efficient nucleation, having efficient nucleation capability. And this mica glass ceramic here, this is very much unique. Here in the last slide we have shown their typical microstructure, because that sealant should have the thermal stability at operation temperature. See, I have shown the processing technique of the material. In the glasses, we have mixed the oxides, and in furnace, we have melt quenched that system at 50 degrees Celsius, and then we have got the glass, and this is the glass transparent, and then we have heat treated glass. The glass we have confirmed from XRD, and this is glass ceramic. The particular crystalline phase, this is mica. In this mica, this potassium ion is electrochemical, is electrovalently bonded with the magnesium aluminosilicate 6. Then microstructure. Microstructure is important because the microstructure shows the bonding capability with other materials. This is the base glass ceramic microstructure, and in presence of silver, this hexagonal shaped mica crystals formed. In presence of gold nanoparticle, these smaller mica crystals, they have the three-dimensional shapes, but they're tiny crystals. The other microstructures can also formed by different nucleation capability. Like here we have shown samarium and gadolinium, sometimes chromium. They have the nucleation capability. Here we have added silver and gold, because silver have their catalytic field strength high, as well as the lattice cell parameter ABC matchable with other mica crystals. This is very unique type of interlock microstructure in presence of ex situ of silver nanoparticle. So this interlocking is very much important, because they can generate this type of interlock kind microstructure and layered silicate structure. From the EDAX pattern, we have confirmed the crystalline phase. Then we have studied the thermal expansion and microhardness for mechanical stability. This is the microhardness value 4.31 and 4.66. This is in situ gold and silver. So this microhardness is okay in the compatible range, but the thermal expansion value. See, this thermal expansion value for SOFC electrolyte, this is yttria stabilized zirconia is 10.6, and for interconnect this is 11.9. So our sealing material should have the thermal expansion value in between these two. Thermal at the operation temperature. Then we have studied the thermal expansion deformation after different cycles. Till 10 thermal cycles, we have found no characteristic deformation in thermal expansion value. Sure. Then we have studied their bonding nature. From heating stage microscopy, we can get that this is the shrinkage value of that sealing material at operation temperature is 7%. That means it can shrink and it can form a compact bonding. And this compact bonding we can see from this interface morphology. Here you can see this is the SOFC anode, and this is electrolyte. This is our glass ceramic sealant. So here no kind of pits, dents, etc. There. This is a compact bonding. And so we have studied the current density and power density for SOFC, and there is no characteristic deformation 7 thermal cycles. So there is no deformation and no crack generation. This is the SOFC stack cell. This is coupon cell we have studied for in situ. This crack is not generated because of the typical microstructure, because from the interlock microstructure a crack cannot generate. If a crack also generated, then that crack cannot be propagated with this type of microstructure. So we can conclude that silver doped glass ceramic possesses very unique kind of interlock microstructure that has the capability for thermal crack resistivity and higher thermal expansion value. For solid oxide fuel cell, we can use the mica-based glass ceramic sealant nucleated by silver or gold nanoparticles. Thank you all.
Thank you very much, Dr. Garai, for sharing your work on uh, nanoparticles doped glass ceramic solvents for solid oxide fuel cells.
Yes.
Thank you very much. I think with this presentation, the presenters from today's list are, I think, over. No other presenters are present. So in conclusion, I will say today in oral presentations, we had presentations of Dr. Mrunal Yawalkar, Dr. Amit Kumar, Dr. Amal Nayak, Dr. Ishita Ghosh, Dr. S. Venkata Ramana Reddy, Dr. Priyanka Bhoyer, then Dr. Vidate, Dr. Saad, and Dr. Mrinmoy Garai. And all the topics were from various diverse fields of the physics, and definitely participants must have gained inspirations from all these talks. So I once again thank all the presenters for showing interest in this conference and presenting their research works. So thank you once again. Now over to Kage sir.
Thank you very much, sir, for chairing this session of oral presentation. So now the session is over, but for tomorrow's day, for tomorrow we shall be sharing the link. Please be at time for the conference. Okay. So now today's all sessions are over. Now with the permission of chair, now we shall stop here. So thank you very much for your presence and presenting nice papers. Thank you very much to all of you.